Okay. So, there's some thoughts I had before we fixed the bug from yesterday. And we're going to go over integer overflow and implicit type conversions. We're going to at least graze over it because that's the problem that is resulting in the bugs in my code. So, before we get to that, I just want to talk about modifier tiles because I think that that could be a good thing to throw into the engine code. So, let's go to my bottom screen here, and I'm on DeviantArt, and I'll show you who this person is. But they made this art about 5 years ago, maybe more than 5 years ago, and I keep on commenting on it because I think it's awesome. But if you look at this, let's see how far we can zoom in. I could see the potential to create an auto tile set that's capable of this kind of thing, right? So we have these auto tiles, right? We can see almost like 3 different materials: this green material, this lighter green material, and this concrete material. I guess there's another material on top of here and whatnot. However, we see like these little divots right here, this divot. So if you consider this and this the same material, how do you get like a divot like this in your auto tiling? So I'm thinking what could be cool is some type of modifier tile, right? You set down an auto tile set, and then right in this region where there needs to be a little gap, you set down a modifier tile. And that modifier tile could be some type of Boolean subtraction operation that alters the topology of the auto tile, right? So this looks really awesome. It's really inspiring because I can definitely see a system where you have auto tiles and you have these different material types and they can layer together and get just a lot of intricacy and detail where it doesn't look so flat, right? It doesn't look like somebody just set down one auto tile material type here and then another auto tile material type here, right? It all merges together in a very nice way, and I think it's possible to make an auto tiling system capable of something like that. And because I think that something like that is possible, I always keep this kind of image in my reference when I'm trying to work towards what I'm building, because I think that this is a goal. I think I can actually make an engine that can generate something like this, but do it in a easier fashion, where it doesn't take as much handcrafted artistic expertise, right? You just create certain materials and then let somebody draw a level with them, right? So this is by, let's actually go to, oh, and also it's like I'm stalking this person, right? Because this is like, I'm the only person commenting on this, but it was like, what is this, 2014? Yeah, I commented first in 2014. I'm like, this is incredible. Then 2017, I came back, and I'm like, this is incredible. Been working on the rendering engine for a few months now. And that was 2017, but that's when I was working on some prototypes. And you know, they haven't been logged in for a while. And then it's like, still 2017, still referencing this image. And now it's 2020, and I'm still looking at this thing. So it's been 6 years, and I'm still like coming back and being like, hey, this thing's awesome. And they probably think I'm a stalker. But anyways, so let's actually look at this person's profile. So RP Whittaker. So this person right here on DeviantArt, I think their stuff is pretty cool. So I don't know if they're active on DeviantArt anymore. 2019. Oh, there's 2018. So I don't know if they're still frequent DeviantArt. But yeah, I really like this person's stuff. So I just wanted to shout out to that. So you know, when you see me, you know, looking at you know, this image, I didn't make this image, right? It's from this person, and I just want you to know that that's where it's from, but it's giving me a lot of inspiration for how I think I can build an engine. Okay, so let's close that, and let's close this. And we're still, okay. So let's get to where I think the problem is, because we've been looking around all over the place, trying to figure out where the math could possibly be wrong, and I just realized what it is. So let's actually look at, well, first of all, let's just run the code, and see what happens, right? Get our bearings. So let's open this containing folder in Explorer, and let's give our build script a run, and just see kind of what happens here. Because I think we left off crashing on an assert statement, if I remember correctly. Oh, I guess not. So, here's what I notice. Now that I had some time to, well, I went to bed, then I woke up, and I had the insight as to what the problem was. And then in the shower, I'm like, oh yeah, that makes sense. I thought about it some more. Surprisingly, I can remember a lot of the details of these certain classes I've been writing, probably because I spend so much time in them writing tests. But yeah, look at these expected values, and now look at these actual values. You know what's odd here? The expected values that are correct are under 255. And then I realized it. My rectangle type doesn't have enough precision. So this PBR here, if we actually look at this PBR, I guarantee that it's probably a 8-bit integer, and it doesn't have enough space to actually address a 512 by 512 bitmap. We need to, before we even get into there and address that issue, what we're going to do is, in the test code that we're writing, we're going to make a little warning for that. So here's what we're going to do. So let's find the test code, wherever it is. I know it's somewhere in here. So this test code here, and we have a case where, you know, we checked all these things to make sure they were correct, and then as we tacked on, so we did this first, and then we tacked on more parameters into this table here, right? We added this x0, x1, y0, y1 for the global rectangular region, for where we're pushing pixels up to the GPU. For that, I decided, instead of expanding this big OR block here, since we already know all the tests work in that aspect, and it's just the new data we're adding on, I figured we'll just tack on this new thing and make sure that these rectangular boundaries correctly match, you know, that they're what we think they should be. And this is where, you know, all if our errors are getting triggered. So here's what we're going to do. I want some type of warning for the next time this happens. So, if actual x0 is less than 255, or actually less than or equal to 255, right? Because 8-bit integer can express 8-bit unsigned integer can express 0 to 255. So if the actual value is less than or equal to 255, and the actual x0 is not equal to the expected x0, okay, we're gonna say printf check for w error. Hold on. No, it's not w error. It's conversion. I think it's w conversion. So I don't have w conversion turned on in my compiler settings, and that's why I'm getting my ass handed to me right now. So we're just gonna say that if we so x0, we're gonna say x0 check for w conversion, which is a very cryptic kind of thing, but let's take this and let's duplicate it a few more times. And the idea is that I'm fixing some kind of, I'm pretty sure that I'm onto exactly what the problem is. And maybe I'm being kind of bold where I'm like, you know, I'm making a big assumption and then I'm going to add all this code and I'm going to be wrong, but I'm pretty sure I'm not going to be wrong. So, we got x0, then this needs to be like a x1. These need to be y's. And actually, let's not do this. Let's not just waste our time doing this. So, let's open up our template. We have a template for finding and replacing things like this. And we're going to take the source here. So, we're going to take this source. And then we're going to look for x0, right? We're going to look for x0, and we're going to place with x1, y0 and y1, right? Okay. Bam. There we go. So now we have to do a little bit of indentation to clean this up, but it's nowhere near as much time as we were going to waste manually replacing each one of those values. So, okay. So we got this x0, x1, y0, y1. So 0, 1, 0, 1, x's then y's, then y's, 0, 1, 0, 1, x's then y's, 0, 1, 0, 1. So that all looks good. Actual and expected, right? And then actual right here, less than or equal to 255. Okay, so that's good. So what we're going to expect is I'm going to expect to actually see this in the console. I'm going to expect to see this as a problem. And, I'm gonna do something like this. I mean, it's not really a... Oh, and also we need a \n for new line. So I'm gonna make it kind of really obnoxious, and that's not proper. I'm gonna make it really obnoxious, like this. And we're going to do the same thing for each one of these, because I'm pretty sure that this is the problem. And we want to, before we fix something, we want to make it more obvious what is going wrong. And what I mean by that is, yes, I thought last night, and then I thought in the shower, and then I'm like, oh yeah, I have the insight, right? But that was only after, like, a whole bunch of debugging and trying to figure things out and being like, what the heck could it be, right? And then finally, after lots of thinking, I finally figure out where the problem is, right? Now, the thing is, if this problem ever pops up again in this code, right, because I do something stupid, refactor something or whatnot, I don't want to have to think, and then eventually be like, Eureka! I want some type of thing that I'm going to put here for myself to give myself a clue as to what happened, right? So, give yourself a clue next time. Okay. So this is what we're going to call this section right here. We're going to call it give yourself a clue next time. Let's move that over there. Give yourself a clue next time, and then we got all these printfs. If we want to indent this, we might be able to do like P for printf, and we might get it. No, because we still got this right here. So we're not going to worry about indenting anymore, even though I would like this to be indented because it's inside of a labeled section. What we can do, though, is we can make note of the current time in this video, right? So right now we are, we can glue this up here, maybe like this. And we can say, like, you know, at video integer ID, and it is, I gotta rearrange here so I can actually see what I'm looking at. Okay. So, the video integer ID is 58, and then we gotta take the timestamp. So, 0058, and the time is 0 hours, 13 minutes, and 47 seconds. Okay. And that's to help me know what this is all about, right? And we actually have to close this off, right? So, so this is a video timestamp to tell me what is this section all about, right? So the idea is that this section, I think I know what the problem is, but I want the console to give me more clues as to what the problem is before I fix the problem, because that way the next time this happens, if I break some code, it's going to be easier to fix next time, because I'm printing out the kind of information that's going to give me that eureka moment again, and I'm going to facilitate making that eureka moment happen a little bit faster next time. So let's give that a shot and see if I see the messages that I think I'm going to see. So, can't believe I didn't make any syntax errors. Maybe I'm getting better at this. So, okay, we got these exclamation marks here. And x0 and x1 are telling me to check for dash W conversion. In other words, you know, warn for conversion problems. And if we look at the printout here, it's the x0 here, and the x1 that are not correct, right? The y0 and the y1, they match, but it's the x that does not match. So I am absolutely sure that I have found the problem. And the problem is, if we go back to our little section topics here, integer overflow and implicit type conversions. I have my rectangle type is using 8-bit integers, unsigned, and they only can address 0 to 255. But but if we look at my diagram here, I'm trying to address a 512 by 512 bitmap. So those unsigned 8-bit integers, they do not have enough space to address everything. And so what's happening is I'm sending off all of my calculations, right? We've checked our calculations. We've checked our calculations everywhere. We've checked our data structures. The data structure looks all right. The calculations look all right. We're looking everywhere, and we don't know what's wrong, and it's because we calculate the correct value, but then, remember, we're talking about integer overflow and implicit type conversions right now. We calculate the correct value, but then, in the thing that we call PBR, for pixel bounding rect, let's go find that up here. When we pass, and we can't even see it here because we assign it, but let's go look where we actually assign PBR, right? So when we assign PBR, a little bit further up. So remember, PBR is just a type def, or a defined for pixel bounding rect. If we go all the way up to PBR, where it's actually being set, right here, I guarantee that the math here is correct. And this UX, well, let's just make sure that this UX has enough space to express that as well, because we could have made the mistake in other places as well. Yeah, so we also made the mistake here. So this is a U08, right? And that does not have enough space to express the values we want to express. So if we look down here, 128 times IX, eventually this is going to overflow here, this UX. So UX needs to be something bigger. So we have the mistake in a few places, and we need to fix it. And I'm thinking that to fix it, we don't really need a int32. That's actually more bits than we need. So we could use a 16-bit integer, and the calculations really only need to be unsigned. However, since the unsigned 16-bit integer is going to give us way more addressing than we actually need, why not make it signed so that we can see if we do anything wrong and things go negative, right? Because integer overflows are a lot more obvious when you see a number that should never be negative go negative, right? Because then you can be like, oh, there's nowhere in any of my calculations do I go negative, why is this negative? And then that can clue you into the fact that, you know, you're doing some type of integer overflow. So I think that's what we're going to do. We're going to, first of all, let's go actually find PBR. So we absolutely know that right here, this is a problem, and we got to fix this. And then in our data structure for this, for the PBR is a rectangle that is for tau sync. So we're not trying to make any like generic data types that are like shared between different libraries. And that's just because I find when I make collections of these generic functions and generic types, I just lose track of the ones that I've made, and then I just get confused. It just gets me confused. It just creates this like God object type of file that has a whole bucket of like random stuff in it, and the only thing tying it together is that, oh, it happens to be reused in multiple places, and that just seems like a horrible organization strategy. It seems like a good organization strategy, but from my experience, it's not. So because of that, the data type for the rectangle, I believe it should be in here, but then when I look in here, I don't see it now, do I? So that is, well, let's just look around, right? We'll find it. So, we know it's this rec thing here. So if we look at our rec type, we'll see, okay, so it's in TauDirt. Okay, so, TauSync is using TauDirt's inclusive rectangle type. That's fine. Like, I'm not going to change that. That is fine because these systems are supposed to be tightly coupled. So having having this tightly coupled like that is fine because TauDirt, TauSync, Tau types, that are all very tightly coupled systems that are all supposed to be very tightly related to each other in terms of functionality. They all work together, so that's perfectly fine. I'm not going to change that. But now let's actually look at it. So, bug hunting macros, hackish debugging, helper recs. Okay, so we have the debug rectangle, and you notice the debug rectangle actually has more size. It has an int32, and that's just so I can, so I had more stuff to work with when I was debugging. But then, when I'm using the actual production size rectangle, I don't want to use more space than I need. However, this can only go up to 255, and we need 512 by 512 in some cases. So, I think that possibly the reason why this is originally only here is because this inclusive rectangle, for some of my math, when I'm only using a local rectangle size, right? So the largest rectangle that's going to ever be pushed up in terms of size is 32 by 32 pixels. So obviously, you know, a 32 by 32 fits perfectly fine within here, right? However, well, actually, let's look where we're using this, right? Because maybe the reason why I have this inclusive rectangle of TauDirt at this size is because originally it was used for local rectangles, and we never had to worry about it being greater than 255, right? It was always in between 0 to 32. So let's actually find this in files, and maybe we will make another rectangle type for TauSync, right? And because we want to use just the amount of bits that we need to use for the different systems here. So define rect struct. This is in TauDirt. TauSync. So TauSync is what we're going to ignore. We want to know that in TauDirt functions, are we doing something that that could lead to some type of overflow? So let's actually just grab all of this stuff, right? Let's just open this. Let's just kind of click, clickety clack. Okay. So yeah, it's in just TauDirt functions. So let's look at TauDirt functions. Now, we want to make sure that we have functions on the right, data on the left. Just so that if you're following along, you know, it makes sense, right? Functions always depend on data, therefore data comes first. That's why I have data on the left and functions on the right. Okay, so let's find the rectangle type in here and see if we are making any integer overflow mistakes here, or if it's just in TauSync we're making that mistake. So, so we got some unit tests, but these unit tests never failed us, so so R, so we have f.x0, min, whatever. So there's some stuff going on here. R1.x0, R2.x0. And then if we look at these calculations here, we're seeing that we have 128 times something, 32 times something. So I guarantee this goes over 255, so we may have made the mistake here as well. So let's look at here. So we got this R1.x0 equals this dot whatever, and then we have these rectangles. So is this rectangle? Yeah. So this rectangle here, if this rectangle is not the debug rectangle, then this is absolutely wrong. So let's look at this and see, well, what kind of rectangle are we working with here? Right, so let's go all the way up and see, well, what kind of rectangle are we working with? Oh boy, so this is test code, so it's probably actually debug rectangles, I'm going to guess. So So, rectangle, what kind of rectangle are we working with here? It's like, I have this insistence to, like, use these rectangles that are, you know, exactly the size I want them to be, and it's like, maybe that's biting me in the butt here. So, rectangle, so it looks like the define is still further up. So let's see, rec. Okay, so the rectangle is actually a debug rectangle, so that's fine. Like, we're not actually overflowing here. But the question is, we need to look for the specific cases when we're using this non-debug rectangle, right? So let's look through here a bit more, and we just want to make sure that this debug rectangle that we are using is not ever going out of bounds. Otherwise, we need to expand how many bits we're using for it. So, clear rectangle, it's taking a struct called rectangle inclusive, and it's a pointer. And the inputs, the possible rectangles we can give it are these rectangles here. Oh, yeah, and those rectangles are, this is like a 4x4 rectangle, this is like also a 4x4 rectangle, this is a 16x16 rectangle, so it absolutely makes sense why we only used the number of bits that we use, right? Because the max that we ever need to get up to is 16x16. We could actually use less bits, but I don't think you can do anything less than I don't think you can do anything less than 8 bits for your integer type. So let's see if that's true. So let's do uint 4 type. Like, I don't think uint 4 type is a thing. C++. Yeah, I don't think that the STD types or the uint 8, 16, 32, 64. I don't think 4 bits. We can go down to 4 bits. Yeah. Yeah, I don't think we can. I don't think this day and age a 4-bit type is not a thing, as far as I'm concerned. So I may be wrong. So a 4-bit type in C99. So let's just look for a 4-bit type. Is there an actual 4-bit integer data type in C++11? Well, I don't care about C++11. Well, I guess we might as well look for C. If it's in C, if it's not in C, then it's definitely not in. If it's not in C++, then it's definitely not in C. So, no, there isn't such type, but you can always use uint8t and bit masking and shifting. Okay, yeah, so that's good enough for me, because, you know, I'm not looking too deeply for this, because, you know, I already am assuming that that's not the case. But yeah, so this rectangle, it actually only needs, like, 4 bits? Yeah, 4 bits, because then we can get, well, actually, no, not 4, because then, yeah, no, 4, because then we get 0 to 15, right? Yeah, so all we need really is 4 bits, so this rectangle inclusive uses 8 bits, so we're already using more bits than we need. However, what we could do is, since we're getting those bits for free, what we could do is we could make this, a signed, just so we have the space for it, so why not make it signed? If we want to maximize our bit usage, we should make these signed 8-bit integers. Because we only need to go from 0 to 15 with our addressing. Okay. So the cool thing is, like, you know, if I'm gonna remake these kind of inclusive rectangle types specific to each class, right, then I can use the exact precision in terms of bits. So let's do a little if-def here. So if AAC 2020 crash on vital to do greater than or equal to 1, then we're just going to put a little note in here for us to remember that we thought this might be a good idea. And if... And actually, since we're kind of like putting a little note in here, what we can do is we can do this. We can actually just kind of throw this in here, and it doesn't even need to be inside of a comment now, because it's just gonna, right? It's just gonna cause a syntax error when this is turned on. Now we might want to make like a proper error, and then just say like C. And technically, this doesn't have to be. It's a preprocessor error, so we actually only have to say like this, comment below. But, you know, maybe I'm being stupid by putting in a string like this, but I don't know, I just like doing it, so I don't know. Whatever, I have some weirdness about the way I write code, and I do things in improper ways sometimes. So we're just gonna say, C comment in source, and then just say, you know, 2020, 12:24, and 11:29 a.m., right? So just a comment that we can find that is unique, right, in the source, and then we can find this. Yeah, but we are on to the problem, and we know what the problem is, so that's awesome. So if we look at this rectangle type, we know that, okay, that's cool. We're using this rectangle here, and these trap values, right, even the trap values themselves, right, we knew that we couldn't exceed 255 here when we originally did this, and that's why we don't exceed 255 here. And if we look at those trap values will be invalid, though, if we, so let's make sure I know what I'm talking about here. Actually, I don't think I know what I'm talking about. What is the range of 8-bit signed integer, right? So it should be like negative 128 to 128, right? Yeah, I don't need to look that up. I know that's what it is. So if we actually do decide to change this here, then we're also going to have to change these trap values. These trap values will have to change as well. So, and if. So let's make a note of that as well. So we'll just say, like, you know, error, trap values cannot exceed, for good measure, it would be best to say can't exceed 127. Either the negative or positive bound is going to be 128, right, because we got 0, so we can't just split it equally in half. So we should probably, to be safe, we probably shouldn't exceed 127. Trap values cannot exceed 127. Error if we decide to use I08 for, and then error. We decide to use I08 for this type right here, right? Then we can't use these trap values here. So, you know. Okay. And this may be a mistake. Maybe we're gonna think that, man, we're being stupid here. And let's make a little note here that the @video integer ID, and this is actually gonna be the thing that's gonna crash on us, isn't it? If you put it here, video integer ID is 0058, and the time is where are we? 0 hours, 33 minutes, and 02 seconds, right? Okay, so we're going to put that here. And then we're also going to put it in the related spot, right? Because we have these two seemingly unrelated... Well, no, they're not seemingly unrelated, right? This is the function file, this is the data file. But we want to make sure that when people see clusters of code that they could find where it was in the video. So we'll put that commentary there, so we know where that came from in the video. Okay, so now that we've done that, we still want to make sure that we're not improperly using this rectangle type. I'm pretty sure that within TauDirt, we're not improperly using it because we wrote tests for this stuff already, and those tests were already passing. But it's just good to make sure of that. So, deepest dirty rectangle, struct whatever, rec ink print, rec ink A and B. What is this about? That's interesting. Is this a, what is this guy? I've never seen that. What is this? Oh, is this like a helper piece of stuff, like, in this file? Yeah, so this is like a... Oh, this is not a struct. What am I... Rec inc a... this is a... Okay, that's not a struct. What am I doing? That's just a, that's a helper function. That's why I need to kind of... You know, I like to do, functions in camel case. So that's why I'm like, that I thought it was a type. That's why I thought it was a type. But, the other thing is, when I write my functions, I like to know exactly what the types they're dealing with are. So sometimes my functions end up looking exactly the way that my, types look like. Like this, we can tell this is a function because we have a capital P. So you can tell that has some camel case in it. And if there's any camel case in it, it is a function, right? So this info any, right? It almost looks like a type, but we see this I is capitalized, right? So the function name is info, and then any is the overload for it, meaning that it takes any type. Okay, so let's just keep on looking at this and see what else we can find. TauDirt, that's not what we wanted to look at. Yeah, I'm pretty satisfied that this is okay here. But I just want to look and make sure. I want to keep on looking around here, make sure that there's nothing kind of suspicious going on here. So we got this rectangle inclusive, and this is just clearing the rectangle with some dirty values. That's fine. Okay. And right here we see this do one thing well function, and the rectangle type we're using is the rectangle that has addressing of 0 to 255. And so let's look for anywhere we're referencing this rectangle. Are we doing something stupid where we're using something out of bounds, right? So this XA, this stuff right here, so these x0s, are they being set improperly? Let's look at that. So, rec512.x0. So what is rec512? It's these rectangles. So no, what about this? What about these? So these values here, well, these are between 0 and 4 and 0 and 16, or 0 and 15. So these guys are within the proper range. So that's not a mistake, right? We're using the very, yeah, that's not a mistake. Min and maxes with those. And these dirty rectangles are in terms of local coordinates, right? Because they're nested inside this quad tree-like structure. And that's why we can have this, like, that's why 8-bit integer is plenty to use for this, right? So when we're looking at TauDirt, and we're looking at it, right, this structure, the quad trees, are, each level of the quad tree, the coordinates that we're using are all local, right? And that's why we can just use an 8-bit integer. But then when we want to turn one of these, when we want to dive into the quad tree and then figure out the global coordinates for the dirty rectangle, those global coordinates need more bits. And that's why TauDirt looks correct, but TauSync does not, because TauSync needs to actually get those bit values. So Okay, so from looking at this, I've taken a quick look at it. We have tests for this code already. I'm pretty sure that that is correct. So what we got to do is, we can close this little note here. In tau sync, we are using this rectangle, and we don't want to use this rectangle. We want to use our a tau sync rectangle. We're going to create this tau sync rectangle that has the proper addressing for tau sync. So we're going to look for anywhere that we see this tau dirt inclusive rectangle, and we're probably going to just remove it and replace it with the proper rectangle. So, like if we see this rectangle, texture update, we already know that this pixel bounding rectangle needs more addressing, so that is wrong. Rectangle helper functions, we got this rec here, and validate rectangle inclusive. That we are also using that's also should be PBR or something similar. So rectangle inclusive and R2. So R2 is actually a R2 is actually a tau dirt rectangle, right? Yeah, because it's these guys. So those are correct. Those are correct because these, when we're traversing these rectangles here, these rectangles are all in terms of local coordinate space in the different sections of the quad tree. And it's when we take those individual values and we start multiplying them together that we have the problem. So, so this t2.ix, that's fine, right? But if we go down to where we're multiplying it together, right here, now we have some problems, right? This UX and UI. Let's make some notes because I'm going to start losing track of things. So, so the to-do, we fix UX and UI need to be at least int 16 types, right, to get all the addressing. And then the other thing we need to do is some of these rectangles need to be so PBR must be a AAC 2020 tau sync rectangle inclusive, right? So these are our notes that we need to address here. So we should probably just consolidate that, right? Because we have like one little notes file here already that we're kind of like putting random notes. So kind of throw that in there. Okay, so with that, and we know that that's the problem. Well, first of all, you're kind of mucking around. Let's make sure that the code still runs, because I'm just paranoid about that. We kind of like put some little, you know, if-def warnings and stuff, and I just want to make sure, okay, so it's still running. I just wanted to make sure that we weren't, you know, accidentally introducing some type of errors. So, we know that works. So, okay, so now that we know that, okay, yeah. So it still compiles, so let's go into tau sync's data, and it's a mess in here. We got a lot of stuff where we're just kind of like debugging, right? And these are also debug variables as well, right? So, I think we don't have enough room here to call this debug variable. I don't know if we can just say like maybe dbg. I don't know. These are debug variables as well. A lot of this stuff is just debug variables. You know what? We have so many like debug variables that we should just kind of like make a section to kind of like know what we're looking at here. So even this number of dirty pixels pushed, that is kind of, it's not as much of a debug variable. Like we could count that as not being a debug variable if we really wanted to, but definitely like everything in this section here, they're debug variables. So we might want to make a note of that and just say, you know, that you know, debug variables, right? And then if we want to kind of like get rid of them, strip them out of the code sometime, we can, but it's going to be difficult, right? So I'm not making it easy to get rid of debug stuff, right? The idea is to test and debug stuff. It's all important for the correctness of the code, so I'm not going to make it easy to take that stuff out, right? We're going to make it hard so that we save it for last, right? When everything works and we need to start optimizing stuff, then we can like start taking out things like this. But for now, we want to like get that debug stuff kind of like really clawed in there, so that we so that we're just we have more certainty about what's going on, right? Nobody's gonna like accidentally set like a define that disables debugging, and then we've been running the project without debugging unknowingly for like a few months, and then, oh crap, we introduced a whole bunch of problems. That's a scenario we don't want, and that's why we're gonna allow debugging variables to just be like, get their claws into the code really, really deep. Okay, so now that we have put that there, so this is, now why does it say unit test? Unit test flag, number of dirty pixels pushed. I guess technically we're using that for unit test. Yeah, I mean technically we are, the whole reason we added this was for unit tests. So I'm not gonna change this section name. I'll add another section name. That's fine. So helper rectangle. Alright, so we'll add helper rectangle section here. Okay. And within here, we're going to call it a struct. And we'll call it AAC 2020 tau sync rectangle inclusive, right? So a very similar name to the other struct, because it has a very similar purpose. And within here, we need more addressing, so I'm going to use like a I16, because if we use we only need 8 bits is not enough. 16 bits is actually too much, so we might as well make it a signed value, so we can detect when things go wrong. When like if there's overflow, we're gonna get negative numbers, and that's gonna help us. So might as well make use of those extra bits somehow, right? Since there's a whole range of values that we're never gonna use, we might as well split that range in half and have, half of the values negative, so that we can garner more insight. Because unsigned values are very error prone, right? Because a lot of the bugs we're getting right now are because we're just being like, ha, we think we're smart, let's use unsigned values everywhere and just get down to the metal and not use any more bits than we need to use, right? And it's starting to bite us, right? But yeah, so when we can essentially get these extra bits for free, we're going to use them, right? We're not going to use any more than what we need, but when we're getting some extra stuff for free, just because, we can't make a data type of exactly the number of bits we need for the precision we have, right? Like, technically what we need is a 9-bit integer, a 9-bit unsigned integer. There's no such thing, right? We got to go to the next power of 2. So we're getting some extra bits for free. We might as well use them, right? Or try to make use of them. So x0, right? It's the same exact structure as all of our other inclusive rectangles. We got our x's then y's, 1s and 0s, right? So I got x0, x1, y0, y1, x's first, y's next, and then 0, 1, 0, 1, right? That's the pattern we use for this. And with that, we're going to have to change a lot of things, but let's make sure that there's a 16-bit type anyways, because I don't actually use 16-bit types, but I'm just going to go with it. So int 16 type. I believe would be what it's called. Fix with integer types. Fix with integer types since C99. Okay, so int 8, int 16. Yeah, so I'm pretty sure there's an int 16. So we're going to go with it. So we're going to go right here. We're going to go define I16. And it's going to be int 16 and then type. And then we're going to make a note of where that is in GCC. So in GCC, it's going to be an stdint.h, which we've already included. And then on here we're going to undef I16, right? And since we're here and we're kind of like using this type for the first time, I might as well make the shortcuts for this. So we're going to go into my shortcuts really quick, and we're going to add that. So let's just do, if we do something like define I16, I'm not expecting anything. Yeah, okay, yeah. And U16 should not be there either, U16. Yeah, so we don't have shortcuts for that, so we're going to do define I16, and I16 define int 16, int 16 define, and then we can't inline this code because it has a hashtag in it, and AutoHotkey does not like that, so we're going to put this in its own file, and then we're going to do the same thing with a define for U16, right? So U16 and U16 define, define uint 16, uint 16 define, right? Okay, and then here we're going to do the same exact thing, except it's unsigned instead of signed, right? So take this, and this will be a U right here, and this will be uint 16, and then we have the note for where that's going to be. So I'm going to take that and put it into a file really quick. So hold on. I'm going to take this and put it into the file it needs to be in. File new. SC files. Shortcuts. CXX. Okay, so this is I16. Oh, wrong thing. Okay, anyway, so hold on. So this is wrong when I named that I16. So new, and let's swap that around. So this is the int 16 one we want to use. Okay. So right here, let's swap this out. So define I16, right? Because this is our int 16 file, and right here is our uint 16 file. And then right here, we're just gonna do U16. Or did I name that U16? No. Okay. Yeah. So okay. So U16, U16, right? And then I16, I16. Okay. Cool. So now that we have these file names, we're gonna put them in their respective places. So I16 is right here. So I16. Then we want to do the same thing with U16. So full file path to clipboard. And we're going to paste the U16 value right here, right? So U16 and I16, right? And then we also need something for undefining them. So undef, and I don't really use this as much, but we want to make an undef as well. So undef I16. And then for that, same deal, we can't actually put it in the actual file itself. And undef U16 and U16 undef. Okay, and then paste line here. So we'll make a note of what it's going to be. So it's going to be like undef and then I16, and there's 2 spaces because I like to keep everything nicely aligned. So undef and then U16, right? U16. Okay. And yeah, that's fine there. I16, U16. So let's actually go and create some files for that. So we have a complementary undef I16. We have a complementary undef folder. So in our snips, we have a folder called define, and then we have another one called undef, which, you know, maybe I shouldn't have had them separated like this, but whatever, that's the way it is. So, I16. Yeah, I16. Okay. And then we need another one for the U16. So, undef, space, U16. Okay, and save that. And we're still in the undef 16, so U16. Okay, and we'll take both of these and paste them where they need to be. And obviously this is a lot of, like, work where it's like, why would you do this, right? But the idea is, it's kind of like sharpening our tools. Like, maintaining our tools can take a decent chunk of time, but then it makes us more efficient as we're going along. When we're in the groove of things, doing all of this prep work is going to make things a lot faster. So, okay, so I just wanted to do that since this is the first time that I'm kind of like starting to use this type. And now we want to make sure that, you know, we're actually going to, you know, use it somewhere, right? And in TauSync is where we need to use it, so let's look for those rectangle inclusives that are wrong. So if we look at rectangle inclusive, and before we do that, we should probably kind of figure out, well, how are we going to... We know that the UX and whatever values are improper. How can we avoid this mistake in the future, right? So what we could do right now, because we know what's going on here in TauSync, we could add some debugging code to make an assertion where we... yeah, I think we'll use some debugging code, and let's just say, you know, if AAC 2020 TauSync macro debug 001. I'm just going to call it macro debug 001 greater than equal to 1. Just enough room. And there's none of that there though. It's a if def, so end if. Okay, so if we are in debug number 1, we're going to add some more code here. So we're all over the place, so sorry about that. Do we already have like any debug flags here? We have debug variables, but they're more like debug member variables. So we're kind of like a little bit disorganized here. Bug hunting defines. Actually, what we have here, we have some bug hunting defines is what we want here. So let's just you know, bug hunting defines. Or we could call them macros. You know, bug hunting macros maybe would have been better. So macro debug 01. And sometimes I call it like bug hunt. Like we call it bug hunt, but we'll probably be out of room if we do that, right? If we call it bug hunt, or really, I don't know, you know, we don't really have to... The most important thing here is that we know it's a macro, and that it's for debug. You know, the specific case of what it's exactly for doesn't really matter too much, so I'm not going to worry too much about, like, being super pedantic and being very super strict and regular with the naming convention here. I think that will be fine here. So we'll just make a note of what we're searching for. Searching for errors due to integer overflow. Right, that's what we're searching for here. And we can make a date here of when we kind of like added this, or not a date, but take the video integer ID and 0058, and the time is 0 hours 59 minutes and 26 seconds, right? And then, since I'm feeling like it, we're also going to use the date right now. So the date is 2020-12-24. Alright, so we got a lot of stuff to, like, tie things up into it. So I really like having the date in my notes because it just makes me kind of feel accomplished, right? It's just a psychological thing where it makes me feel accomplished when I, like, see notes and I'm like, oh, man, that was from a few years ago, right? And then you're like, man, I've been working on this for a long time. Look at that note, you know? It also probably has some type of utility, but this is mostly a psychological thing, and the actual utility is just right here. But we're going to do that because we have enough room to write it out in one line, so sure, why not? So for this debug variable, we've turned it on, and what we're going to do is we're going to trigger a runtime assertion error, or halt or something, but we already know that the mistake is right here. It's in other places as well. But the first mistake is right here because we had a UO8 value for the this right here. That's a mistake, and it's overflowing. So what we're going to do is we're going to check for overflow by using an int32, right? We're going to use an int32, and we're going to call it UXCHK for UX check, and then an int32 for and actually it doesn't need to be it can be unsigned integer. None of this should be, well, you know, we have enough bits for it. We have enough bits for it, so let's keep it signed. Sure, why not? And then, you know, UXCHK equals, and then it should be, it's going to be T0.ix times 128 plus, now, I'm not sure how that works with the casting. Like, I think that we might want to, like, expand the range here. I think we might want to do I32 like that. So upcast it like that before we start adding them together. Just to be safe, we probably should do that, just in case. And then we can... Yeah, there we go. So yeah, just to be safe, we want to wrap it in a cast just to make sure that it's correct. So, so really that's not even correct there because we want to wrap it. We want to cast. Well, IX is. Yeah, we wanna do something like this. We wanna. Okay, this is getting ugly. It's getting ugly, but it's like we want to make sure that everything is working properly, right? So we're gonna make it ugly because we just want to make absolutely sure that our math is not overflowing, right? So we got this int32 128, and then over here int32 cast of these values, and we got ix. So T0, then we got T1, and then multiplied by 32 here. And then, lastly, we're skipping this part because it was too granular. And so these are the only two things we're adding. And for this plus here, I think I also want to wrap it one more time. So, right, so just be very paranoid, right? You know, operator precedence, you know, is going to catch this, so it's not like we really have to worry about it, but just in case. And yeah, that's kind of ugly. It's kind of ugly, but you know what? It'll work. So this is our check value. And then we have this UI check value as well. And all we got to do for that is change the x's to y's, right? Okay, now that we have these check values, what we're going to do is we're going to say that, you know, if UI, so we're going to say I32, right? We're going to cast it to an int32. If the int32 UI is not equal to, and also, since I don't do this very often, I might as well just be careful with my casting. I'm sure that that the operator precedence binds closer to the cast than it does the not equal operator, but I want to make absolutely sure that I haven't made any stupid mistakes, right? Because the whole problem with the code right now is because of a stupid mistake, right? Where we have this implicit type conversion that's biting us in the butt. So we might as well say, well, if the problem was due to a stupid mistake, then maybe we should write the code with making more stupid mistakes in mind, right? So I don't want to make some stupid casting mistake when we're checking for a stupid mistake, if that makes sense. So, so if this is a problem, then we're going to say that so we'll say, like, if 0 or this thing is wrong, right? Or this thing is wrong, right? So we're gonna take the x's and the y's. So here's our x's, here's our y's. Then we have a problem. So we'll halt. So we'll do like an error and integer overflow 2020 1224. Integer overflow tau-sync. Now, that could be not a unique enough message eventually, but for now, it's unique. And then within here, what we're going to do is we're just going to say, you know, if either one of these is incorrect, we'll just do a printf of the individual values now, right? So ux and the ux check value, right? So ux and then colon %d \n and then ux. Okay. Ux and uy. And then we want another one for the check value, right? So, and we called it uxchk for check. And then since we're doing that, we might as well just call this actual, right? Just so that it lines up a little better. And this is ux, and it's going to be chk here. Okay. And so, by the way, we know what the problem is right now. We're just fixing it, right? We're making the code a little bit more robust by shoving in a whole bunch of error checking, and it also makes the code much more clunky. But the thing is we found this problem, and before we fix the problem, we want to make the code more robust to detect this problem, right? We never want the same bug to pop up twice. Okay, so we have not implemented this inclusive rectangle yet because we're trying to trigger this integer overflow error, right? So let's give that a run and see what we can derive here, right? Expected declaration specifier something something. Okay, I probably didn't put the yeah, so I'm like, I even named it macro, but then I didn't do a define. So define, there you go. Okay, so now that we have this, let's give that a run and see what we can derive here. So UO8 tau sync unit test flag equals 0, error expected, blah blah blah, or blah blah blah. What the hell? I'm gonna guess that I forgot. I'm missing a semicolon somewhere. That's what that error kind of looks like. So let's see. It's on line 39. Man, I just can't do this. Line 39. Like, I might have made a mistake up here, right? And then it's leaking down into here. Right? Like, that looks fine. Line 39. That looks fine there. It's just... Oh, yeah, because structs need a semicolon, but functions can't have a semicolon. It always wrecks with my day. So, okay, yeah. So, I haven't made that mistake in a while, but just did, so... Okay, so let's see what we got here. Okay, so what do we got here? Integer overflow, tau sync. Excellent. So we got the check value for one of them is 256. but the actual value is ending up as 0. That's awesome. So, right, we added this extra code, right? It does make everything super clunky, but now we've nailed down where the problem is, and now we can kind of like, so now that we have an error that kind of checks for this problem, what we're going to do is we're going to fix that, right? We're going to fix it right now by expanding this type here. The type for this only needs to be a 16 bits. We'll use an I16, int 16, because we have the extra room, so we might as well, 16 bits is more than enough. It's plenty more than enough. So we might as well use a signed type. So let's take this and do I16 right here. I16. And then right here we have to define it here somewhere. So we have this I32, U32, U08. I guess it makes kind of sense right here. So define I16, and then it's going to be int 16 type, and it's in GCC std int.h. Okay, now we have to move everything around, so that's great. So we thought we were done doing this, maintaining this big list of stuff, but apparently not. So how are we going to do this? Well, I guess one step at a time, right? So we're going to, bam, take that, we're going to shift that over, and then this is going to be 6 now. It wouldn't be as hard if we didn't have this kind of weirdness here, but 6, 7, 8, and 9. And then we can do 10, 11, 12, 13, 14, 15, 16. Yeah, everything is kind of ugly over here. So 17 now. And let's go down to the bottom of GPU sync, right? And is this int 16? Int 16 type? Yeah. Okay, cool. So that's correct. Then down here at the bottom, we're going to add it in the same place. So we have the U08, and it's the 16-bit, so we want to put it in between here. So undef int 16. And then we're going to shift everything up. Okay. So let's take all of this, paste it here. Then this is a 06 now. This is kind of tedious. It's like, maybe I should rethink doing this, but like I said, we're only writing the code once. It's going to be read much more than it's ever going to be written. So, I'm going to take the time to do some of these tedious things because I just want something that's nice and solid, 13, 14, 15, 16, 17. Okay, cool. So now that we have that, what we're going to expect is we're going to expect to run, and that specific assertion is not going to trip anymore. So what do we have here? Expected identifier or something before... So obviously I don't know how to write code. That's what this means. So let's look at that line again. We obviously screwed something up. Yeah, so... yeah, that would be a problem. Okay. So now let's take it for a spin and see what we've fixed, because we're hoping that we fixed it. I don't think we fixed everything, because we still have some more refactoring we have to do to get rid of this problem, but we're closer here. So yeah, so we have this error again, right? So we're not halting on that section of the code anymore that we were previously at, because we fixed that. But there were more mistakes we made in that code with the size of our types. And we can see, once again, these match, but these don't match, and that's why it's telling us that it's probably a W conversion problem. That's fine. So we're getting closer. And it's not like, this isn't the hard part. This is actually easy now, because I know exactly what's going on. So if you look at PBR, pixel bounding rectangle, pixel bounding rectangle needs to be that other type now. So pixel bounding rectangle, okay, this is just the variable, and is a rect type, and right now we're using this tau-dirt rectangle inclusive. And we don't want to use that type here. And also, where else do we not want to use it? Where are we using it in this file, and do we want to use it in all the places that we're using it? So we see this rectangle for texture pushing, helper functions, validate rectangle. So this one actually is the dirty rectangle. The kind of rectangle that we're validating right now is so that so because this is not a tau sync rectangle that we're validating here, it doesn't belong in here. It actually belongs in it belongs in tau-dirt. So if we look at it, right, these rectangles here that are being validated right here, that we were like double checking, all these rectangles are rectangles for the quad tree. Yeah, so like R0 and whatnot, like these rectangles right here, that's actually the type they need to be, because that's what the data structure is. And if we look at rectangle, tau-dirt rectangle inclusive there, so we need to take this check here, and it needs to be put into the other file. So let's put that. So tau-dirt. So we have to change this to tau-dirt as well. So tau-dirt, and we need to open up the tau-dirt function. So tau-dirt. Okay, so tau-dirt's functions here. Console padding, log after halt, min-max helper, rectangle utility functions. So that would be kind of in here. Inside something check, tau-dirt rec inclusive print. So rectangle utility functions looks like the place where it needs to be here. So rectangle utility functions, yeah, we want to put it in here somewhere. I think that's the best place for it. So we're going to take this thing right here. We're going to cut it out. We're going to move it here. We're gonna do that. We got rec. Air is the only macro we don't have here, is it? Yeah, air. And this is already tau-dirt rec inc, and we have it up here as well. Yeah, tau-dirt rec inc. Yeah, so this is where it belongs. We even have CHR already. But air is not going to be tau sync halt. So air right here, we're going to define the air macro. So define air AAC 2020 tau dirt halt. Okay. And then down here, we're going to undef air. Undef ERR. And then we can clean up these macros that are kind of around what we pasted into here. And rect validation. Rect validate used by tau sync. So it is kind of weird that it's used by tau sync. So I just want to make a note that rect validate used by tau sync .f. Right. We'll make a little note about that in the section, right? To make a note of, you know, okay, because that is actually where this belongs. Now, because we kind of like pasted this in here, and now it has this like new level of indentation, we kind of have a problem with this kind of like going over the edge. And so the way to fix that, I guess, let's just make that a little bit terser, right? There we go. Equal OK. Equal OK, don't use greater than or equal to, right? You can keep that same kind of commentary. And this thing here, I don't know. We're just off by just a little bit. You know what? We're just gonna say we're gonna take this right here and just do like tau dirt 2020. I don't know, just something there. And then here we can make the note for what that means. So you know, we can make the note of what that means right here. And then use it right there, right? So inverted rectangle, and then the name of the rectangle, and then the error message, right? So we could line that up nicely so we can see this. Sure, whatever. That's good enough. Now this is on one line. I don't know why I had 2 semicolons if it's on one line. Okay, so we shoehorned that in there and made it abide by our formatting rules. So that's good. That's where it needs to be. So this is no longer called tau sync validate rectangle. This is now tau dirt validate rec inclusive, right? And you know, we could also make a note that at vid iid 0058, and then the time is 1 hour 21 minutes. 1 hour 21 minutes and 28 seconds. Moved out of tau sync.f and renamed func. Right? So we moved it out of tau sync and we renamed it. So you notice that this commentary kind of applies to the top of the function. But with the style I've been going for, I'm like, well, I don't really use IntelliSense, so I'm not going to put stuff on top of the functions, because it looks cluttered to me. It looks hard to see what I'm looking at when I put comments on top of function names. So I put the commentary for what functions do actually inside of the functions. Okay, so that looks good to me. That's like, I think that refactor should be proper. And we're still expecting everything to crash. We just kind of like moved this into its proper spot, right? And then over here, we're just going to take this and we're going to say that we're going to make a note here, right? We're going to just make a note of what happened. Keep like a keep a paper trail, you know? So tau so this tau sync was renamed to and moved into tau sync.f. Right? So function right, so if we look here, oh, we gotta close this off first, so I don't think we refactored those names yet. So if we look at tau sync validate rec inclusive, yeah. So we renamed it and put it in the space that it actually applies to, which actually makes it a little bit more readable, right? Because when we look at this code here, we think validate rect inc, and we look at tau sync, so we think this is a tau sync type of rectangle, but it's actually a tau dirt type of rectangle, right? So by properly namespacing it out, we can garner more information about the actual types of data that we're working with. So we'll do tau dirt, and tau dirt for that validation code. And we'll give this a run, make sure it's still crashing in the same place, make sure everything's still compiling and all that good stuff. Okay, cool. So still crashing in the same place, but we're getting We're getting closer. We're just kind of slowly, we know what the problem is already. We're fixing the problem, but we're kind of slowly making provisions to make sure this doesn't happen again in the same class or the same library. Okay, so now, PBR. We have a problem here because now our rectangle types, we have two rectangle types. This pixel bounding rectangle is not the same rectangle type as this, right? And we're gonna have to, you know, what are we gonna do? How are we going to accommodate that? I think the way we're gonna accommodate it is, because I'm sick of writing all these type defs, is for pixel bounding rect, well, we know what type it needs to be, so let's just write it out long-handed, right? So the pixel bounding rectangle here needs to actually be the AAC, actually struct AAC 2020 tau sync rec inclusive, right? This is the actual type that we need for this pixel bounding rectangle, right? And now let's look at where pixel bounding rectangle is actually used. And we see pixel bounding rect PBR. Let's highlight both of these so we know that they're kind of the same. And math and all that stuff, assigning things. You got this UX plus whatever, blah, blah, blah. So here was the problem right here with that overflow. So to check for that, actually, let's go back to the pixel bounding rect. Let's not change it just yet. Let's not change it just yet, because let's actually detect the overflow that's happening there first, right? So let's keep this as a rec type, and we're going to fix it. Let's make sure I didn't make any syntax mistakes. We're going to fix it, but first we're going to add the debug code to properly detect the overflow we think is happening, right? Before we fix it, we want to add some more code to make it robust, right? Every time we fix something, we don't just want to fix the problem. We want to make the code more resilient to that problem in the future, right? So, let's hold on. Okay, so let's take a look now. And I lost my train of thought. Hold on, let's just run this again for a second here. Okay, so yeah, so let's go into here, and we're in TauSync right now. And in TauSync, we have this, like, macro debug thing here, right? Let's use that to debug the pixel bounding rect calculations that we know are improper, right? So we had some asserts, so we were trying to find some problems before, and we couldn't because it was overflowing and then wrapping around, and so the bounds checks just kind of completely failed. So we have these calculations, and all we're gonna do is say that in here we're gonna be like if AAC 2020, oh boy, AAC 2020 tau sync macro debug 001 greater than or equal to 1, and then end if. Okay, so right there. And we're just going to declare some more variables, right? We're going to, like, add, like, int32, PBR, or, we could do, like, expected x0. Let's make sure there's no expected x0 anywhere in here. There probably is, but it's probably in the unit test code. Yeah, inside the unit test code, we do have this already. That's fine, right? The whole thing is that, we want to be as regular with our variable names, so it means the exact same thing as it does in the unit test code, therefore giving it the exact same name is a sensible choice. Expected x0, and then, we'll create these as well. Expected x0, and then x's and then y's, and zeros and then ones. And expected x0 dot, well, it's not a dot, it's just that, expected x0 equals, we're actually just gonna take these exact formulas, and we're just gonna, bam, paste them right in here, right? And replace the PBR with just expected underscore. And the next thing I might want to do is, I really wish we could indent this some, but we're kind of like running out of room, aren't we? Well, we could indent it more, right? We could, right? We could just, right? But if we indent it more, then this formula doesn't look exactly like that formula. And that's what bothers me, right? Like, I like the fact that this is exact, right? This is exact, right? It's an exact match right now. And that way, you know, without a doubt, you can be like, these are the same formulas. Now, if we try to condense the formatting here, we're not going to see that. So if we want to do it, if that's what we want to do, then we gotta condense it over here as well. You know, if that's what we want. But for now, let's just deal with the ugliness, and just say that, you know, if expected, let's say I32. Or actually, expected is already at I32. So if expected x0 is not equal to PBR, or U32 PBR dot x0, we already know this is a mistake, right? We already know this is actually happening. So I'm not going to worry about, now that I think about it, since I already know this is happening, I'm not going to be too worried about making absolutely sure that these casts are correct. Well, actually, maybe I'll make that an I32 at the very least. But we're going to expect this error to get triggered. Once we make this check here, I'm going to expect the program to crash here. And if it doesn't crash here, then I'm going to be a little bit concerned. Because I'm pretty sure that I'm honed in on what the problem is. And if this doesn't crash, then that'll worry me, because I'm fairly certain that I've honed in on the problem, and so far I've been correct. So let's do error, PBR, integer overflow detected. Right, so that's what so for the pixel bounding rectangle, we've detected integer overflow is what's happened. And, do you want to actually print off the things? Sure, why not? Expected x0 %d \n, expected x0, paste that a few times, and then take these right here. And then we want to do the same thing, but with PBR dot whatever, you know. So this PBR dot whatever here, we're going to take that, and we're going to put it, like, right here. And right here. Okay, so it's obviously, this is very cluttered, right? So we got more debug code than we have, you know, normal code, right? So it's like, that kind of sucks, but, you know, that's the, whatever. You know, First priority is working code. So, you know, as much as I want code to look pretty, sometimes it just gets really ugly. So, okay, so we got this debug section. It's ugly. It's guarded, so eventually we can turn off this kind of debug logic if we end up with a performance problem, but we'll leave it on for the remainder of the project until we're at, like, a final product that we can actually, like, use. And let's give it a shot, right? Let's hope we wrote everything correctly, and if we wrote everything correctly, we're going to expect it to crash right here and get this error, right? So let's give that a run and see what happens. And if that happens, then we're pretty close to fixing it. Then we got to fix up our tests, and we're good to go. So no syntax errors, so that's cool. Okay, PBR, integer overflow detected. We got our expected values, and we see that the expected values, we have a 256 and a 257, but then the actual values, we're getting our 0101. So excellent, excellent. So we have, we've solved a very major problem in the code. And I'm glad I added extra tests. But also, I need to add just the flag warning for conversions, -w conversion, I think it's called. But right now, when I add that flag, it picks up on a problem in load PNG, which I included in my project, and so I need to get this to stable state before I go into load PNG and kind of hack it up and add the correct cast or whatever I need to add to fix the problem. And then once I fix the problem, I can address it wherever else it is in my code. And then in the future, we won't need as much debugging for this kind of mistake, because we'll have the compiler catch it for us. But in the meantime, while we're, playing with the safeties off, messing with all these different integer types and mixing them around, and making stupid mistakes that are, like, almost impossible to find, in the meantime, we're just going to have to do this kind of stuff, right? So now that we know that, PBR is overflowing, now we can go back and change its type and expand its type, right? So this PBR, right, it's the wrong rectangle type. We're going to delete that, and then put it to here. And we'll make a note here. So at vid integer ID and 0058, and the time is 1 hour 36 minutes and 09 seconds, right? And just make a note that we were previously using an AAC 2020 tau dirt rec inc. We can get rid of the AAC 2020, right? We're inside of this library. I don't think anyone's going to be confused about that. The library prefix is mainly for people who are including the code, right, in their projects. We were previously using, well, now it's an A tau.rec inc, which can only go up to 255 for each member. PBR, pixel bounding rec, needs to be able to address a 512 by 512 space, because that is our texture size. Created tau sync rec inc to fix this. Okay, so that's the basic idea. Lately I've been kind of liking the extra space I get and the extra, like, cleanness I get from writing comments kind of like this. Right, so I can still kind of enforce that there's, like, this boundary, but it's not as cluttery, right? And then also down here I can go like this. So now we can kind of, even though we don't have the kind of same section divider that we have with like this kind of stuff, like this section divider that accurately marks where the code begins and where the code ends, right? At least this kind of helps us know that, oh, we have these stars here, we have these stars here, and we have these stars here. So I just absolutely want to make sure that, oh, crap, 21 people? Oh, geez. Okay, thank you. Did not expect 21 people. So yeah, I just found out the problem from yesterday. The problem from yesterday was integer overflow, because I'm an idiot. We don't have a flag called -w conversion on right now, because load PNG Load PNG has some problems that need to be fixed with that specific warning before I can use that warning in my project. So I've been kind of like playing with the safeties off with my data types, and I've been bit in the ass 3 times so far, where I'm like scratching my head for hours trying to figure out where the problem is. And we're in the middle of fixing that, and just adding bounds checks and things. So one of the important things is when we fix something. So actually, let me break it again. Let me break it again. So here's what we do. So if we break the code and say that this is a rectangle type, and let's give this a run for a second, and I'll show you what I mean. So, and if anybody wants to see like actual visual demo of some shiny stuff, I got some more shiny stuff for everybody. If people want to see some shiny stuff. So anyone want to see shiny stuff, we'll show it to you. Okay, so you see this little error message that says PBR integer overflow detected? I added that after I realized what the problem was. So if we go and look for overflow, the word overflow, so I was like, oh crap, I think that, that's another error there. Let's look for the other thing that says overflow. Overflow. Okay, so I was pretty sure that these values here were doing integer overflow, right? So since I was pretty sure these values were doing integer overflow, I'm like, before we fix it, right, before we expand the number of bits in these variables here, these member variables, before we do that, before we fix the problem, we want to make the code more robust to protect against the problem from happening again, right? You know, it's a very common thing for the same bug to pop up multiple times in a project. Like, somebody fixes it, and then a month later, the same exact fucking bug comes up. I think that's stupid. We should try to prevent that from happening. So, since we're like, oh crap, this is probably overflowing, we need to, these are only 8 bits, and it needs to be like at least 9 bits. Of course, there's no 9-bit type, so we're gonna have to go up to like 16 bits. But so we know, so we're pretty sure it's overflowing. So before we expand this and fix the problem, we're going to add some debug code, right? So we're going to add a debug macro here for debugging, and we're going to do the exact same calculation here. So this exact same calculation, we're going to do it over again, but we're going to use int32. We're going to use a wider type, and then what we're going to do is we're just going to say, here's our expected values that we calculated using int32s. Here's the values that are int8s. We're going to upcast them to int32, and then we're going to make sure they match, right? And if they don't match, we're going to say that integer overflow is detected. And so, in my code right now, when I run my code, we can actually see that. We can see a little warning, or not a warning, we actually crashed the game. So it says PBR integer overflow detected. Okay, so now that we've added this extra code, this extra big clunky boy, all this code here, to guard against that from ever happening again, now that we have actually fixed that, now we will actually change the type of this PBR, right? So now we'll go backwards and actually address that variable where we declared it. So right here, we used a wrong rectangle type. This rectangle type, every member of the rectangle is 8 bits. We need a rectangle type that has at least 9 bits, so 16 bits is what we'll have to go for. So we're going to use this rectangle type that has a wide enough data type for each of those members. So now that we put this in, it fixes the problem, right? So when I run, there's still some more problems, but we know what the problems are. Incompatible pointer type, pixel bounding rect. Oh, so I'm actually mixing the wrong type. So I actually have to refactor a few other things as well. But let's take a look at this and fix it up. So, pixel bounding rect, and that's on 555. So let's look at line 555 for a second. So some of the things are going to need to be refactored because we're using we're swapping in a different rectangle type. So 555, where are you? 555. I should just use G for go to. So we have this push command for pushing a pixel bounding rectangle, and it's a macro for this function. And let's go into this function and see where that is. So, okay, this function right here, we can see that it is taking the wrong type of rectangle. It's taking a rectangle called tau dirt rectangle inclusive, and this rectangle is for traversing our quad tree. That rectangle in tau dirt is for this quad tree, and all these cells, the highest cell value you have here on the X is 3, like 0, 1, 2, 3. And then, because it's only a 4x4, this is a 4x4, and the cells here are 16 by 16, right? So you have plenty of space when you're traversing this structure to only use 8 bits. But when we want to figure out the global coordinates of one of these dirty rectangles to push the actual pixels up to the GPU, well, our bitmap is 512 by 512 pixels, so we need more than 8 bits, right? So all we got to do is we got to take this rectangle inclusive define here, and we just got to swap it out, right? Because the pixel bounding rectangle needs to be the bigger type. And so we can even see kind of a mistake here where even the namespace doesn't quite make sense. So we're going to change this to tau sync like that. And like I said, if anyone wants to see something shiny, shout out, because I'll show you some more shiny stuff. I know that this is kind of boring stuff that I am working on. So yeah, tau sync, and let's give that a spin and see if we can get this running here. Okay, so we are, we're back to, yeah, we're good. So, I mean, the test is still failing, but I'm on the next test now. Because it says row 9. We were originally on row 7 when we were failing our tests. And now we see that the expected values for this are 0, 0, and 0. It's just because I haven't filled out those values yet. So that's excellent. That means we've honed in on the problem, and we can start to write the rest of the test code that we were writing yesterday before we kind of got stuck. So let's close this right here, and I don't know if we want to close that just yet, but let's go down to our test code, which is kind of like all over the place. So I'm just going to type row 7, because I know that that's kind of related to the name of, is this not tau sync? Maybe that's not what it was called. Let's just scroll down to our debug code, our unit test code. So at the bottom of the file, I kept all my unit test code, because unit tests sometimes get out of hand, especially when you are kind of like when you have a problem in your test code, right? When you have a problem in your test code and you start grasping at straws and you don't know what the heck is going on, then you start to just add code all over the place, being like, maybe it's this problem, maybe it's that problem, and you just start adding a whole bunch of code in your test, and then your tests just like explode. And so I always keep my unit test code at the bottom of the file, just because it just gets out of hand really quickly. In fact, it got so out of hand the past few days that you see this unit test function. Well, here's a unit test for 1221, here's unit test for 1222, and here's a unit test for 1223. And I'm actually glad that I wrote this last chunk of unit tests, because I was delirious when I wrote these tests, but they all passed, but I was like, I'm delirious, maybe I should write more tests tomorrow. And so I did, and then I found a mistake, and I'm like, that's crazy that I wrote 2 chunks of unit tests. These are large functions here. I didn't find the problem, and then I'm like, I was delirious when I wrote this, so let's just add one more for good measure. And I thought I was just going to enjoy myself and just be like, you know, we don't really need to do this, but it's better to be safe than sorry, and I want to try out this new way of writing tests, so why not? And then I found a problem. So let's go into here. So you see all this green right here? This is a unit test table. So we're writing all of our tests in a very terse way. I did not do this for the previous tests from the previous days, because this can be very error-prone to get set up and working correctly, because these are our inputs, and these are our expected outputs. Inputs, expected outputs. So this is the first test, this is the second test, this is the third test, etc., right? So we just packed everything into a large array, and then we just run it as tests, right? And the advantage of this is we can get really, really terse, and we have a kind of a bird's eye view of, like, all of the tests that are being ran, right? We can, what is that saying, like, not being able to see the forest through the trees kind of a thing? Well, since we've written our tests kind of like in this very dense way, we can kind of see the forest. We can kind of get the big picture of what we've been trying to do. So we know that it was 8 and 9. 8 and 9 right here, these tests are now failing. And we have to figure out, well, what's the correct values for that? So the first thing is when I was writing these previous tests and doing the math, I just added these offsets here. I had calculated these offsets, and then I was like, once we get this test running, we're going to condense the math, right? We're going to remove these pluses and just add everything together. So we're going to remove this 0 plus 288, and we're going to just move it over here, right? And, right, because I don't want to go past my column. So, 288 plus 5, so 193. Now I am paranoid that I'm going to do something stupid, so even though it's simple math, I don't want to make a mistake, because, so I am going to check on a calculator, just to make sure that, that it's what I think it is. So, 293, not 193. What am I doing? So 293. Yeah, let me check one more time. 288 plus 5. 288 plus 5. 293. Okay, so this should be 293. And the reason I'm going to compound these back to single values is because a lot of times the next chunk of tests applies a translation or something to the previous expected the previous inputs or something, right? We apply some type of translation. That way we don't have to do too much heavy lifting with the math when we're trying to get new test cases, right? Sometimes we just want to translate the data and make sure that the calculations come out, right? Like if you have some calculations that should not change if the data is translated, then you want to translate the data and see if you get the same outputs. And that's kind of what I'm doing in some of these tests. So then we have 3 plus 192 and 192 plus 3. So this is 193. And 192, so this is 195. Okay, 195. Okay, so now we're going to make sure that we didn't screw up anything here, right? We're going to make sure that tests 6 and 7, or not 6 and 7, sorry, tests 8 and 9, indices 7 and 8 are going to pass, right? Because we just did something, we just kind of condensed those numbers. We want to make sure we didn't make any stupid mistake. Okay, so we see that, oh god, we made a mistake. So we have, so it looks like the second thing I made a mistake on, we have actual 291, and we have 293 here. Because we already know that this test was kind of like correct, right? We already knew it was correct, and we just kind of like refactored it and made it wrong. We're just going to we're just going to be like, well, this is the actual value, this is the expected value. The expected value we know is wrong. So we're going to change the 293 to 291 for number 7. So number 7 here, 293 needs to be 291. Oh, because these, okay, yeah. So let's do, and this probably also needs to be 291 as well. We probably screwed that up as well, right? Or maybe not. That's probably 291, and that's 293. Let's give that a run. So, you know, I make stupid mistakes, and that's why change a little bit of code, compile, change a little bit of code, compile. Because never underestimate how many stupid mistakes you can make, like not even being able to add. So row 7, we have actual. The actual is 293, but we need 291. Okay, so hold on. So let's look at row 7 here. So row 7 right here. So this should be 293 right here. 293. Oh, did I swap them? Is it supposed to be 293 and 291? I don't know. Let's keep on running it, and hopefully that we can get this going. God damn it! I can't believe I made it. This is why I broke out a calculator, and I still wasn't careful enough. Okay, so 291. So row 8. Okay, just screw this. Control Z, Control Z. Abort, Control Z. Okay, get back those. God damn it. Okay. Put that back. Run it again. Make sure that they're not failing. And then we're going to do it in smaller increments. We're going to... obviously, that was too much for me. Okay, yeah. So now we're on row 9. Okay, so let's actually take this. So let's take the obvious things. Right? So we're failing on row 9. Let's change this. Right? Anything that's plus 0, that should be pretty obvious, right? So let's... it's a plus 0. We'll just do that. And even though that was obvious, we're still going to check it, right? We're still going to check to make sure that even though that was completely trivial, and we're like, why would we fuck something up like that? Well, we know why we would, because we just did it like a few seconds ago. So we're gonna kind of slowly fix this, right? So we see 1 plus 192, that should be a 193, right? So 193. And 192 plus 3, that should be a 195, correct? So 195. Okay, we're going to run it again, make sure that our simple arithmetic is correct, because for some reason we're just not that good at math. Alright, so, yep, we're still failing on number 9, so the current tests that we're refactoring, these are tests indexed. This is index 7, and this is index 8, these numbers here are actually checksums. For counting the number of tests I have. So, okay, so we have 5 plus 288, and 3 plus 288. So let's actually break out the calculator, and let's just do, 5 plus 288, which we already had, 293, right? And I think what I did was I may have put 293 in both spots, I think? I don't know. Well, let's just do 293. And let's do it one thing at a time, because I don't want to... I just want to be careful, because I don't want to have to go back and correct this again by making a mistake. Okay, so that's still good. And then the last thing is, 3 plus 288. So let's throw that in there. 291. Okay, 291. Okay, so now let's run that, and we're expecting that test to still pass. Oh, and like I said, I know... those of you who are still around, like, I can show you some fancy stuff. Like, if you want to see the shiny stuff, I will show you shiny stuff. Because I always can enjoy a break as well. Okay, so row 9. Okay, yeah, cool. So we got that fixed up and condensed. And now we're gonna kind of like, we're gonna change the spacing here because I'm OCD like this. You'll notice that I never go over my column limit, right? I have a very strict column limit, and I never go over it. So... actually, you know what? After I get this fixed up, after we write these tests, so we have 2 more tests to write. After I write those and they're working, I'm just gonna show you shiny stuff anyways, because I know that some people are kind of shy to like speak out and whatnot. So, and I could enjoy a little break after kind of finding the problem here. Okay, so. Let's make absolutely sure that I didn't do anything stupid while reformatting. I'm just very paranoid. Okay, yeah, so still crashing there. Excellent, okay. So now, let's look at this. We're not in the same headspace we were yesterday. The whole point of trying to finish these tests yesterday was because then we got to figure out, like, what all these values mean and what the calculation should be. So we see copy tests 8 and 9. So 8 and 9 here. And test diagonal cells on the edges. Okay. Now, if we have 6 and 9, and we're just like... So, 6 and 9 here. We have 6 and 9 and 6 and 9. And I see we have like this 12 and 17, 12 and 17 here. So what we're doing originally in tests 8 and 9 is what we're doing is we're saying, okay, go into cell 6, and then once you're in cell 6, you're going to go into cell 9. And then once you're in cell 9, you're going to place a piece of data either at index 0 or index 17, which is right here, right? Because index 17 is here because we do that. From here, we add the stride of 6. If we add the stride of 16, we're going to end up down here. And then if we add one more, we end up here. So we go diagonal, right? So the idea is that we have these index values that can be abstracted into XY values because we're mapping this over like a 2-dimensional grid. but we don't have any space to really, like, do index to XY math in here, so we have to actually just, like, do these correct stride calculations in our head and, like, hard code them in here. And that gets to be a little bit much, but let's look at this and kind of figure out what we should expect. So let's look at 11 and 14. So 11 and 14 is 11, 12, 13, and 14. So 11 and 14 right here. Let's actually figure out... So each of these is 11 and 14. Let's do some calculations. So to figure out the translation to get into the global upper left corner of the update rectangle, we need to take 11 from the first quad tree, or the first quad-like tree, and we're going to multiply that by 128. Or, no, we're not. 11 needs to be... We have to figure out the xy value of 11, right? So let's look at 11, right? So 11 right here, the xy value is 0, 1, 2, and 3. So it's 3 on the x and also 3 on the y as well, no? 0, 1, 2. No, it's 2 on the y. So let's just throw this into our notes really quick so that we can look at it while we're doing this. So when we are looking at 11, global x is going to be 0, 1, 2, 3, right? So 3 times 128 plus, and then let's get the other diagram. Let's just keep on copying and pasting so we kind of know what we're looking at. So the next level of our quad tree-like structure is this, right? So we're at 11, and then the next level is 14, right? The next cell we're picking is 14. And 14 is 11, 12, 13, 14. It's this right here. So the x value here is 0, 1, and 2, right? So it's going to be 2 times 32, because each of these cells is 32 by 32. And then for the offsets here, we have those diagonal cells. So we should probably do like a global x1 and or a global x. I don't know. It doesn't need to be a variable, so we could put a number in front of that. This is just to help us kind of figure out what's going on here. So I'll just say this is the test 10 global x that we're kind of calculating here. And we see that we have this 2 here. We have these 2 cells right here, don't we? So we're not going to calculate all the way. We're not going to calculate that last offset. We're just going to calculate this offset first. Okay, so global x, and then the global y should be kind of flipped around. Like, I'm actually expecting the global y to be like 2 and 3 like this. And if we look at 11 and 14, let's look at 11. So 0, 1, and 2, yep. And then for 14, 11, 12, 13, and 14. So this cell right here, we got 0, 1, 2, and 3. So yeah, 3 times 32. Okay, so these are our global offsets that we need to use for our test here. So let's take these, throw them into a calculator, because we can't be trusted to do math, and it's been proven earlier. So let's take this, throw it into a calculator. Okay, so we got this like 448. Okay, take that 448. And in our notes here, we're just going to say, this, equals, 448, right? Then for this, we're going to take this, throw this into the calculator. So we have 352, right? So 352. Okay, so these are the offsets that we're going to need to apply. And let's take a look at the test. So we have 11 and 14, 11 and 14. So for the offsets for the x and the y, we have both of the offsets we need. Now, these numbers here already had those offsets applied to them, right? So, copy tests 6 and 7. Really, is this copy test 6 and 7? Because, yeah, 6 and 7 here, and then we applied the offsets. So if we look at these tests will probably look kind of similar. So in these tests, we see we have a 2 and a 17, and the test we're currently working on is a 2 and a 17 as well, 12 and a 16, and then all this stuff. So to me, what it looks like is... Oh, but this is 5 and 5. I think we're just going to have to... do the math. So let's think about it. So we got this 448, and there's no offset here, right? Because we start at 0. So for the upper, so these should be the correct upper left-hand corners of the dirty rectangle, because the first pieces of data that we're setting are at 0, 0. Why do I do... Okay, so if that's our assumption, then if we're honing in on that and we think that this is correct here, let's plug that in for the x and plug that in for the y. So this is x0 and this is x1, and we can confirm that really quick in our diagram. So if we look at our little diagram above the data sets, we see x0, x1, y0, y1, and that's just a consistency of how I order my variables. Always x's first, then y's. General to specific, so the general category is it an x or a y, and then the specific category is it a lower bound or an upper bound? Lower bound being x0 being the zeros, and the upper bounds being the ones. Okay, so yeah, we're just gonna throw these in here because we think that this is the correct x and y for those for the top left corner of the update rectangle we're going to use to push the section of the texture to the GPU. So if we're correct, we should kind of see that feedback in the test when it fails, right? The test is still going to fail because we got to fill out those other values, but I think those are the correct values for the upper left-hand corner, and we just kind of want to whittle away at it until we kind of get it. So we're close. We have 448, but then we have 453 here. Well, we had this 352. So what did we do wrong with the math? So it looks like we did the x math correct, but then the y math is not correct. So the x was correct, but the y was not correct. And why is that? So let's open up our little calculations here. So the x's is correct, 448, but then the y's are not. X's and y's. X's and y's. So what we're going to do is we're just going to have to look at it again and think about it. So this is wrong, huh? Okay, well we got 11 and 14. So 11 here. So on the y, that's going to be 0, 1, and 2. Okay, so 2 times 128. Okay, yeah. And then for 14, we need to know where 14 is in here. 11, 12, 13, and 14. On the y, that's going to be 0, 1, 2, and 3. So that should be 3 times 32. Maybe the math? Well, that's not cool, man. 352, yeah, okay. So is there something else I'm not understanding about this? Yeah, that's not, oh boy. So now I am... Really, 448 and 352 is not correct. Are we somehow multiplying by the wrong thing, or... Is our diagram wrong? 11 and 14. 11 and 14. 1, 2, 3, 4, 5... 11, yeah. 0, 1, 2... 0, 1, and 2. Okay. 14 is 10, 11, 12, 13, 14. 14, right? And this is 15. So 0, 1, 2, and 3. We got our 2s, we got our 3s. In fact, the formula is we even have the symmetry here, right? Where we have, we kind of knew that the 2s and 3s would just be swapped, right? That's what we assumed. Yet... Ah, man, that's infuriating. I wonder if we have just more, like, integer overflow problems in some other place I haven't detected yet. Oh, hold on. It's off by... It's only off by 1. 453 and... Oh, I'm being stupid. I'm being really stupid. Okay, so... this is the lower bound x, or the... Sorry, this is the lower bound x, or the... This is the x for the upper left corner. Lower bound x. This is another x value. So I'm just not paying attention to what I'm looking at here. So since we have a 0 here and a 2 here, then what we're going to expect is, if we look at our diagram, one of our diagrams here, let's take this over here. Okay. Let's just paste this. Can we just kind of paste this in here? Come on. Come on. There we go. So if we put something here at this nesting level, there's no extra offset applied. But if we do a diagonal here, then it's one offset on each axis, right? So if this is the correct x0 value, then the correct x1 value, the correct x upper bound value, should be it's one cell over, but each cell is 2 by 2 pixels. So it should be this value, but we're going to add, I believe we would have to just add 2, right? Let me think about that. Oh, it's not quite adding 2. It's, so if we look at what we're actually looking at, let's try to visualize it. Okay. So let's expand it a bit. So when we're talking about the cells, when we are talking about, like, putting one dirty value at this 2 by 2, we're putting it right here, and we're getting this value right here. Well, if we go kitty corner to over here, we're going to end up putting a chunk of pixels down here, and we want to get that lower corner. We want to get this lower corner. So the offset between here and here is much larger. So if we can count, we can go 0, 1, 2, and 3. So we actually have to add 3. So 448 plus 3. So that's going to give us 451, correct? Yeah, 451. Okay, so now let's check to see that both of those values are correct in our test. So let's give that a run. And then after we get these 4 tests done, I'll show you some shiny stuff. Okay, so now we have 448 and expected was 451. Can I just not... Actual 448... and 451, huh? Hold on. Let's check our math again. So I'm pretty sure it's just it's my understanding of what I'm doing that's wrong, not the code. Like, I'm fairly certain that the code is now correct, and it's just me not in the correct headspace from yesterday. So 448, and we got this 0 and 2. Oh, crap. This is not diagonal. This is diagonal, right? This is 0. This is our diagonal case, but we're not looking at our diagonal case. We are looking at our... So the diagonal case is the next test. So the diagonal case, we could actually put this down here for the next test, because that's actually the next test. But, because that's the diagonal. So we can actually take this. We've kind of solved those. But right now, the test is actually... we're setting something here, we're skipping over this and setting something in the next cell. So actually what we're looking at is we're looking at, for the x values, we're looking at this, and then we're skipping over one of them, and then we're going over here, and so our x0 is over here. So our x0 is over here, and then our x1 is this guy right over here. So the correct offset is 0, 1, 2, 3, 4, and 5. Our correct offset is 5. So 448 plus 5 gives us 453, right? 453. Okay, so now let's look at that test. Okay, so we got 448, we got 453. So these two things right here match. Excellent. So now let's solve this part here, right? So let's solve the y's now. And you can see that we kind of like already, but previously we did all these tests already, but we kind of like packed on, as an afterthought, we packed on these extra things to test, and then lo and behold, we found a huge problem, so I'm glad I did it. It was just I honestly wasn't going to do it. I'm like, oh, we'll save this for later, but then I'm like, you know what, if we try to save adding on these things for later in our test code, we try to come back to it months later, we're not going to be in the correct headspace, and it's going to take us much longer to kind of figure out what these values should be. So I'm like, man, it's going to be more efficient just to tackle this now than to do it later. So I was like, I'll just do it now, and then I found a huge problem. So I'm kind of glad I did that. So, okay, so now let's look at those y values, right? So our y values are calculated right here, because we have the 11 and 14, right? So 11 is 0... Oh, the y values, sorry. 11, 0, 1, and 2, right? So that's correct. And then the for the next nesting level in our quad tree-like structure, we have a 3. Wait, not a 3, sorry. I'm making shit up. So this 14 over here, the 14 from over here, this 14, 11, 12, 13, 14. This is cell number 14, and on the x, sorry, on the y, it is 0, 1, 2, and 3. And we can see we have a 3 here. So, and that's 352. Let's just double check that, because do not underestimate your ability to do stupid stuff. So 253. Okay, it is 253. So now what we need to do is we need to just throw this in here. So this is the y0. So this is the upper left component. The upper left of the dirty rectangle in global coordinates, and it's the y value of that upper left coordinate. So this should be correct. This 352 should be correct. So let's test it out and make sure that it echoes back the correct value. That 352, we should see that as the expected and the actual when we look at the set of data. Yeah, so 352 and 352 as well. So the next part should be pretty simple. We know that the first piece of data is set here at 0. We skip over cell 1 and we set the next chunk of data here. And so that means that on the y, y nothing, right? Because we're not going in that direction. We're going in this direction, which means that we just have to add 1, right? Because this is the upper bounds and this is the lower bounds when we're talking about the y's. And so all we got to do for this is we got to add 1 to this value. So we're going to paste it here and we're going to add 1. And then this test should be done. And now it should say that it's going to fail on row 10, right? Because this is checksum number 11. It's the 11th test, but the row index is 10. So let's give this a run and hope that we see that it is now failing on row index 10. I'm all out of tea. I need some more tea, but we'll do that later after I've kind of showed you some shiny stuff. So yeah, so now the row index we're failing on is 10. And we did have the correct guesses earlier that this was 448 and 451 because we were solving for the wrong variables earlier. So let's solve for this, and then we can keep on going. And we have, once this test is done, we have 2 more tests that we have to solve for, right? So let's look at the situation we have on our hands. This is our diagonal test, right? We have 2. And, oh, not 2, sorry. We have 0 here, and then 17 here. So that is 0, and then 17 is over here, because we add the stride. Remember, this is a 16 by 16 cell, cell quad tree-like structure we have here. So if we want to get diagonal here by using the indexes rather than the x's and y's, we got to take this coordinate, we got to add 16, because that's the stride, and then we just have to add 1, and then boom, we're diagonal, right? So to expand on this, and this is an overlay, right? This is a 16 by 16 overlay of a 32 by 32 chunk of pixels. So when we're looking at this cell and this cell, if we expand that into pixels, what we have conceptually is this and this, right? So our upper bound is right here, and our lower bound is right here. So when we see these numbers right here, all we should have to do is add, what, 3 to it? So we have 0, 1, 2, and 3. All we got to do is add 3. So 448 plus 3. So that's going to be 451. Okay. And then... Oh, that's kind of confusing that they're the same value there. That's throwing me off. And then for the... Oh, hold on. Make sure I'm comprehending this correctly. This is x0. This is x1. Sorry, this is x0 and this is x1. Yeah, I might not be thinking of this correctly. Hold on. Oh, no, because this is already the +3. This is already the +3 going on. So... Let's take this. This is the correct y0 value. This should also be the same y value here. Let's paste that down there for a second. We got a little too ahead of ourselves and got confused about what our variables were again. So let's just paste that down there and make sure that all matches. And then it's going to be easy to solve for. So yeah, those match. So yeah, okay, cool. So okay, we're good. So this 352 is y0, and to get to the y1. We have to go 0 plus 1 plus 2, that's x, sorry. Well, it's completely symmetrical, so it doesn't really make a difference, but if we're looking at the upper bound y, right, we're here, for the upper bound y, we got to add 1, 2, and 3 to get that lower bound y. So this 352 needs to have 3 added to it, and that's going to make it 355, correct? So let's add 3, let's make it 355, and then let's hope that that math is correct. Okay, yeah, we're on the next test, right? Because all these things are zeroed out. That's a quick heuristic for me to know that we're on the next test, because sometimes looking at the row number will confuse me, because I'm like, I have to keep on thinking to myself, okay, it's the 0 indexed is the 11, and then, but it's the 12th test, right? And I always have to convert that in my head. I always get confused. But yeah, so we're on the next test. So let's go look at what that needs to be, right? Because once we get this, we're done, right? Once these two tests are in, we are done testing this Tau Sync system. So once we get these two tests written, we just got to figure out what are these 4 values. Once we get these 4 values, we're gonna show you some shiny stuff, reward ourselves because we figured this out, and it's been bothering us for at least 3 days of writing tests. So, or actually, this is my 4th day of writing tests, because I'm coming back to this test function that has this date. But that was yesterday, right? That was yesterday. So this is actually our 4th day writing tests, and I'm kind of sick of it. But this 4th test we wrote, or this 3rd test we wrote, found some problems. So I guess you could never have too many tests, I guess. Okay, so let's look at this and see, well, what is the difference between this chunk of tests here and this chunk of tests here? Well, thankfully for us, we have some comments. Copy test 10 and 11, so we have test 10 and 11 here, so we just copied them, and translate var location 3 over. Okay, so let's think about what the implication of translating the var over 3, right? So we have this chunk, and we're just gonna like translate it, 1, and then 2, and then 3, right? Not quite like that, because this is supposed to be 32 by 32 cells. Sorry, this is supposed to be 16 by 16 cells, but we don't have enough room to draw the whole diagram, so we wrote these little dots. So really it's 1, 2, and then somewhere in the void of the missing parts of the diagram, right? But if we look at the values here, we can highlight certain values. Oh, or not like that. We can highlight certain values and kind of get a quick little diff here, right? And be like, what is different, right? And we already know it's different, but let's just sanity check it, right? So anything, so these are all the same, and we see that it is the translation, right? This is T, S, and V, T, S, and V. So it's the variable cell that has the different values on it, right? We've translated everything over 3, like the comment says, right? So we added 3 here. And then for the 2 and 17, we also added 3. And the advantage of doing that is, right, because these cells here for 0 and 17, they're like diagonal, right? And so to do another test with the diagonal, I'm like, I don't want to have to rethink that for a diagonal that's like translated somewhere over here. That's going to be difficult for my brain. So instead of that, we're just going to shift everything over to the right. And as long as we don't wrap over the 16 cell border, the math will still work out, right? Because we're using indexes here. We're not using x's and y's. We're using indexes. But as long as we don't shift by too much to the right, we can just add to the index and it will just naturally shift over the x value without affecting the y. Okay, so what are we expecting to get out of this? And I guess what we're expecting is we're just shifting over the cells by 3, right? So let's take our little cell diagram here. And just say that, you know, everything was kind of like here, but then we decided to add 1, 2, and 3, right? So 1, shift over 1, shift over 2, and shift over 3, right? So everything that was here, everything that was here, let's do this for upper and lower bounds, everything that was here is now going to end up here, right? And we are shifting over only on the x. So we only have to change those x values. The y values should actually be the same, right? Because we're only shifting over on the x, right? The y positions have not changed. With that said, if that's the assumption that only the y values have changed because, you know, we're translating over horizontally, then we should be able to take these values from the previous test and we should be able to just throw them down here, right? If that's correct, right? And so let's run the test and make sure that these values actually match, right? We're going to fail on here, but we should see that these two values just match, right? So let's take a look at that and see what we got. Okay, so we have 353, 353, 352, 352. So they match. Okay, so we just got to figure out these last two. So let's take a look at that. Let's look at our diagram. What is the offset, right? So if this is 0, then it's 0, 1, 0, 2, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7. Okay, so from here to here, we got to add 6, right? From here to here, also add 6. So we just have to add 6 to these values right here, and we'll be good. So we just got to take 448 plus 6. Also, got to make sure that we note that these two values are different, right? These two values are the same. So let's just do 448 plus 6 first. Okay, so we got, oh, by the way, I see I have a 9th viewer that just popped in. We are almost done with this last test case. We just have to figure out what these 4 values are, and then our tests are done, and I'm going to show people some shiny stuff, because I took some more animated GIFs of the old game that I'm trying to build a new engine for. So you can sit tight, and I'll get to that. So 454, huh? So 454 and 454. 454, 454. Okay, so let's run that and make sure that these values are correct, and then we have to figure out what these zeros are, and then we're done. So let's okay, so 454 and 454, excellent. Okay, so the next thing is 453. We're adding 6, right? We're adding 6 to everything. So 453 plus 6 is going to make it 459. So let's make sure that works. All right, we're going to do it in small incremental steps, just because I'm very good at screwing up minor details. I wish that was not the case, but I am. So we have 454, 352, 355. Okay, so we just gotta change that last value and we're good. So this should be this 451 plus 6. That just gives us 457, right? Okay, let's give that a run. Excellent. All right, everything's back up and running. Okay, so let me give you a quick since, you know, we rarely see what's up here. It's nothing that fancy, but let me explain what we're working towards here since we have something kind of up on screen here. Okay, so the project is built up in a very linear fashion. Just because this is C code, and sometimes you can do like really stupid stuff in C code where you just get like really weird behavior and you don't know why it's happening. So I built up the project in a very linear fashion, and one of the first goals was just to get a basic shader and record the mouse position, right? And then build on top of that. So I created a class called like a shader testbed. And each number key that I press gives me a different shader testbed slot. So this is shader number 1, shader number 2, shader number 3, 4, 5, 6, 7, 8, 9, and 10. Or actually, there's no 10, sorry. There's no 10, this is 0. This is just the 0 slot for there's no shader loaded, right? So for shader number 1, this will be the shader that is reserved for rendering subsystem number 1. Shader number 2 will be reserved for subsystem 2. This is just something I stole off of Shader Toy. It's not the actual subsystem code. And then shader 3 for system 3, shader 4 for system 4, and etc., etc., etc. When I press the number keys, I get a different subsystem. We're keeping the key bindings as simple as possible. So until the project is very advanced, very far ahead, we're going to always keep the top number keys reserved for switching between the different systems of the game. The game is editor-centric, so that means that every single system is actually an editor. And when we're playing the game, we're just playing the game inside of an editor that does not allow us to edit the level, if that makes sense. The reason for having the editor and the game be the same code is then we don't have to maintain editor code and maintain game engine code, right? They're one and the same, right? We don't have two code bases to maintain. Also, sometimes if you have an editor and then you have a game engine and they're two separate things, you'll have this problem of, oh, it looks one way in the editor, but it looks a different way in the engine, right? And that's a huge problem that I've often had, and I don't want to have that problem. So we want to eliminate two problems. One, we don't want to maintain two code bases, and two, we don't want to have that problem of it looks one way in the editor and looks a different way in the game. And to avoid that kind of problem, we just make the editor and the game one in the same. And we basically just, when we're playing the game, with that, whichever editor ends up being the game, we just lock that editor. We lock certain features of the editor, saying, okay, now that we're actually in the game mode, you cannot click and drag and edit tiles, right? So let's go over kind of like, well, first of all, before I show you the shiny stuff, I need to do a git commit, a git commit here, because I just passed those tests. So git status, git add dot, and then git status again, just for a sanity check. Okay, and then git, hold on. Yeah, okay, and then git commit -m for message, and just say tau sync unit tests all finished. Okay. Then git push GitHub master. Okay, so now let's show you kind of like the stuff I've been working towards. Take a little break to show you that. And also I think I'm going to be called to dinner soon, so I might as well show you that kind of stuff that I'm working on. First of all, I gotta find the folder that I put it in. So CodeTuts, AA2. Okay, hold on. So let me look for this. It should be in... oh, I know where it is. It's in my E drive. It's in my vital assets. Don't hack me. I don't remember which one it's in here. Hold on. Let me check around here for a second. Is it in my HD? I don't know if it counts as HD. I guess it does. Okay, cool. So, found it. Okay, so I added some more stuff. I think we started at 23 is the things I added since last time I showed people this stuff. So, let's just open this up in a little, in our, like, Windows, whatever the heck. And let's go to animated GIFs. Because I made, like, a little thing for it. See, isn't that cool? Bam! Let's zoom in there. Animated GIFs. Okay, anyways. So, the way this game works, and maybe, like, you've all seen this before, because I know we had, like, 20 people kind of stop by, but maybe when people raid, I should probably just drop what I'm doing and be like, here's some interesting stuff. I'll keep that in mind for next time, to just drop what I'm doing. If Heroes still here, thank you for bringing people my way. So, basically, it's a game where you have these proximity mines, and when the mines, you touch the mines, they light up, and then they blink, and then after they've been tripped for so long, they explode. So they don't explode right away when you touch them. And so you basically are setting traps. Oh, the only exception are these skull bombs. Skull bombs are instant kill bombs, so if you touch them, they will immediately explode. Different bombs explode in different directions to help us, like, create interesting chain reaction kind of patterns. So there's a vertical explosion, a horizontal explosion, and a small four-way explosion, which is these little orange bombs you see. And then these skull bombs are large four-way explosions. So these skull bombs kind of have two purposes. One, they're instant kill, and then also they're used just to have a bigger four-way explosion radius. The reason why we needed bombs that have a bigger four-way explosion radius than these small four-way explosion bombs is because for these small bombs to chain together to, like, create a chain reaction, they have to be directly next to each other because the explosion radius only goes out one cell from where the bomb is. So they have to be right next to each other to actually cause a chain reaction. But it is kind of fun because then you create this chain fire that kind of, like, follows you. You kind of see, like, that chain fire that's kind of like when I go in here, it creates this chain of explosion that kind of follows you, and then you're like, oh shit, gotta run. Let's go to the next kind of GIF here. So we also made, like, hold on, is this the right thing? Yeah, sure. So, right here, this is a level design from our Rush level set, which is basically you have to get out of the level before it closes in on you and kills you. So right here, you can see, if I didn't make it in time, the wall would have collapsed on me. So this wall right here is about to fall down, and it's about to eliminate my ability to get up to here, right? It's about to come down here, and it might crush you, and if it doesn't crush you, well, you're going to sink into a bottomless pit, right? Because the floor is about to blow out, right? The floor is going to blow out, and then, well, there's some other animated GIFs of that are a little bit better. I'll have to do another one later. So let's go to here. So in here, we made some kind of, like, bulldozer kind of things that they just kind of, like, they're just little AI that kind of, like, add a little bit of pressure to the level. I do think that I did record this so that I beat every level that I recorded, but sometimes there's more than one try because it's been forever since I've, like, done these levels. So we'll just wait till I finally kind of, like, beat this. Yeah, kind of escape down there and then kind of jump up over there, right? The lighting engine, like, you're seeing all this fancy kind of lighting. I did that lighting engine. Oh, nice. Okay. So I did the lighting engine. Let's go to the next level. So, sometimes the solution to a puzzle isn't quite obvious, and depending on what kind of solution is needed for the puzzle, it needs to be categorized into a different level set. So, to change the difficulty of the game, we don't actually, like, change how much health you have or the dynamics. We just change the level design, right? So the solution for this is kind of, like, subtle, right? It's just like hide right here and then let this falling wall just kind of pass you by, right? And now you can kind of just, like, go on by. And actually, I don't know if that was the intended solution or not. It may have been like a dexterity challenge where we have to, like, blow out these bombs and dodge them and get down here before the wall comes in on us. And I just didn't realize that I blew out part of this, right? Right? Like, it may have been a... So sometimes you have an intention for how the level's supposed to be solved, but there's so many complex things going on that inevitably you or even your users find some, like, really hackish way to, like, beat the level as it was not intended. But the thing is if somebody finds, like, a quicker way to beat the level that was not intended, that's totally valid. That's awesome. I think that's awesome, and that kind of makes this game kind of really good for, like, speedrunning, right? So let's keep on going. And I see I have 24 people following me. I don't know how to, like, keep track of, like, notifications, because I don't know how to use Twitch. But, I do thank everyone for, like, following me. I'm sorry that I haven't, like, called anyone explicitly out. But, you know, I'm a friendly person. I do appreciate it. And, you know, if you have any programming questions or whatnot, and you need some help with something, feel free to ask me. If I know the answer, I'll kind of give it to you. So this is kind of like another kind of pressure thing where you have this wall that's going to fall in on you, and you have to bust open this and get down here and get to the exit before you get crushed to death, right? So crushed to death, blood decals for where you die. So the intended solution for this, I believe, was to run down here and then run across here before the floor gives out. Because there's this giant piston right here, and this giant piston, it comes down here, it hits this piece of glass, the glass has a little bit of delay before it shatters, and then the piston hits these bombs right here, and then the floor gives out, because it causes this big chain reaction, the floor gives out, and you have to make it before that happens. And there's no safe place to hide, right? Because up here, you're going to get crushed to death, and you can't wait down here because the floor is going to give out, right? And it doesn't look like I solved this in this GIF. There might be, in the next GIF, I might have a GIF of me solving this, or it might be later, because I know that sometimes I accidentally recorded things wrong and had to go back. So let's go to the next GIF. Am I at the next GIF? I wasn't paying attention. Are these both, like, kind of the same? Oh yeah, 27 and 28 are... So 28 must be where I'm solving it. Let's take a look at this. So I'm probably solving it here. So, right, take a ride down... Oh, well, or try to take a ride down there. So I'm solving it in the way it was not intended, but it's the quickest, easiest way, right? You just take a ride down on this piston, and then the floor gives out, and you have to try not to get hit by those explosions that are going vertically up, but if you're right in the center, you can dodge them, or if you jump early, I guess. So, let's go to the next thing. So, this was infuriating. This was more of a... So, different level design offers different things. Like, some level design can be completely infuriating, where you have to be very slow, methodical, and it's very tedious. And this is a very slow, methodical, be careful, tedious kind of level. And I actually hate this kind of level. I don't like this level. What I really like for levels is I like levels where it's just like everything is coming at you really fast, and it's like, oh shit, things are exploding, and you just gotta dodge things and react quickly. I don't really like this kind of methodical kind of thing. But the thing is, different people like different things as far as a level design goes. So, what we did is we wanted to say, well, this engine in this game mechanic is capable of making a lot of different styled levels. So let's group our level designs based on the style of play people like, right? Like, if people want slow, methodical puzzles, we can make like a puzzle set for that. So we can make a whole set of levels just for that style of play. If people actually, there's another style of play that I really like. It's called just it's kind of a stupid style of play. And it's not in any... It's in some really old prototypes that I don't know where they are anymore. But the style of play is just... There's two buttons, and you have to press the right one. And if you press the wrong button, you die. And if you press the right button, you live, right? So, basically, you press a button, and a series of chain reactions happens. And if it was the correct button, it blasts open a way to the exit. And if it's the wrong button, the series of chain reactions kills you, right? It signs your death warrant. And maybe I could find one of those examples in some of the very old... I'm going to look for on my DeviantArt if I can find a very old example of that. So Deviant, because I'm pretty sure we have an example of that, because we were like kind of showcasing that in the really old prototypes. So let me see if I can find a very old prototype that a very old image that kind of has that feature. So, so I'm pretty sure... So this is... I haven't really used this DeviantArt in a horribly long time. So this is some of the engine aspects for designing tile sets, fractal-based tile sets for the new engine. But I think it's in my gallery. Hold on. So I'm going to search around. Actually, let me put a new GIF while you're waiting for me to find stuff. So... I'm not going to be able to explain it while I'm looking. Interactive. Oh, God, I had interactive demos. Oh, no. Animated. Yeah, animated category. That's what we want. Okay, cool. Yeah. Here we go. So let's let's show you some of the very old prototypes, which are much more shiny. I actually like the shininess of the old prototypes, but my artist didn't like them, right? So the pistons look a little bit different, obviously. Everything's kind of like, whoa, neon, and my game designer did not like this. They're like, well, this is too shiny, I can't focus. I really like this. I thought this was fucking rad. And so the next time once we're working up to making this engine again, we're gonna have like 2 modes. We're gonna have like a sane, not so epileptic mode, and then we're gonna have like this like crazy strobe mode, because I really liked this mode. I'm like, man, this looks fucking awesome, man. So you might notice that the character can actually break blocks with their head, right? So they can actually, can I zoom in here? Let's make another screen really quick for DeviantArt, because we have this screen here for animated GIFs, but it's not aligned because this is DeviantArt now. So I'm gonna make a quick a new scene for this, so you can kind of see more of the detail of what's going on here. So my microphone's gonna turn off really quick because it's a new scene. Everything's gonna turn black, but don't worry, I'll get everything up and running really quick. So I'm just gonna make a new scene. I'll see you in just like a few seconds, so hold on, please hold. Okay, so I'm gonna call the scene Dev Art Anim GIFs. Dev Art. I'll call it Dev Art GIFs. Okay, Dev Art GIFs. Alright, so hopefully you can hear me again. I'm gonna add some of the images to this, so hold on, black screen again, but we have sound now. So now I'm gonna add a display capture. Okay, add this display capture, that's the one we want. Okay, now we're gonna crop it. I'm gonna crop this display so you can kind of see what we're looking at here. So, properties, not properties. What do I need here? Cancel. I need a filter, right? Filters, and my windows are all over the place. So, please hold. It's very hard to like navigate here because OBS kind of like is not very friendly to people who have multiple monitors. What I've noticed. So, okay, there we go. So now we can start cropping this down. So let's say, let's try 200, 300. That looks a little bit too tight. Let's try 260, 270. How about 280? 280? How about 285? How about 290? 290 is pretty close. 295? That's pretty close. Let's stick with that. And then let's go on the right-hand side here. Crop that out. Let's try 300. How about 600? Closer. 640 maybe? 640, 650. That looks like we need maybe 660. 670. How about that? Yeah, that looks pretty good. Okay, so now let's crop the top. So let's do like 300. Oh, too much. 200. Still too much. 100. 120. 140. Yeah, 140 looks about right. Okay, and then let's take this and say, I don't know, 300. That looks like too much. 200. 230. Right, this is a lot of guessing and checking, so I apologize. 220. So how about 225? How about 226, 27? So, yeah, we could probably make it 230, but that's good enough for us, so let's close this. And now that we have kind of an image here, we can kind of go, bam! We can kind of zoom in on that, like that. And then let's kind of label what we're looking at here. So, this is... let me get some text here and label what we're looking at. Okay. And select font. Okay, this is... let's center that. Okay, so that's what we're looking at here. Alright, there we go. This will be for next time, so that's what we're looking at. Awesome. So the old prototypes, you notice that the tile sets kind of look different. And I actually like the bomb design here for these things because the bombs kind of indicate what direction they're going to explode in. But it was kind of like a thing between where I didn't want to like I wanted the artist to kind of enjoy what they were doing, so I let them kind of make some decisions that maybe I regret with the bombs. But, you know, I wanted them to have fun with it, so I wanted to, you know, we're a team here, we're just doing a fun project, you know, if the artist's vision for how things should look is this, then we're going to go with it, right? So basically I said, okay, I'm doing the engine programming, you're the artist, I'm going to give you full reign of, you know, how you want to do the art, right? And this is their vision, and the tile sets are their vision. The stroby craziness is kind of my thing. But then the game designer was like, no stroby craziness, so we got rid of that. Let's go to the next thing. Because we wanted an example of kind of like a level where, well, this is really simple, right? It's very basic, right? Go from one door to the other door. Originally I wanted to be kind of a survival horror kind of look to it, so that's why everything is kind of dark and stuff. Right, a little skull blowing out its teeth by going through the bombs there. Let's see, what about this guy? Oh, great, so it's not even completely centered for this, is it? Whatever. So this is kind of cool level design idea, right, where the floor is really jagged, and it's going to take a long time to cross there, but if you hit this button, it blows out the floor. It makes everything nice and level, right? So we got these jaggies, and then the pillars fall, and then you can kind of just run across it nicely. Same thing with here. So we were trying to think of this game as like a time trial game where you could have little hacks, or, oh, if you press this button, it makes the level quicker to traverse, right? So let's look at what else we got here. So these are very old prototypes, so you notice the actual level design. There's different level designs. I've lost track of a lot of the level designs. And I wish I mean, it's all backed up in, like, GitHub, but some of the code is, like, broken, so I have to, like, go back to, like, previous commits, and it's in Flash developed, so I have to recompile, so a lot of this is pretty lost, and it's like, whatever animated GIFs and things I took of these old prototypes are kind of, like, what I'm stuck with, in terms of, like, these demonstrations. So I'm glad I did take a lot of GIFs, but I kind of wish I had taken more. So this is kind of a pick one button or the other kind of a thing. It was really made, I'm pretty sure the intention was to only press this button here on the right and never press the one on the left, because this was like one of those simple level designs that I really like, where it's like, press one button or the other button, and if you press the wrong button, you die, right? Dead simple, but just kind of fun, right? Because you just get to press a button and see if your guess was right, and if your guess is wrong, this fancy chain reaction happens and it kills you, right? So this was supposed to kill you, right, where you hit this button and, you know, the floor blows out beneath you and you're dead. But I think one of my play testers found a hack around that. It's like, oh, I can just jump on top of the button and I'm safe, right? So originally it was supposed to be a choice between two buttons, but some people, they got really aggressive with the game, and they were like, you know what, I'm a 100% kind of person. I wanna press both of those buttons and exit the level, even though the design was originally just press one button, pick the right one. But you got these overachievers that, you know, they want to, you know, press all the buttons and make it through the level. And that's fine. I mean, I'm not going to tell you how to play. So let's see, over here, right, more like kind of fun little chain reactions, right? We made like this little exploding spiral. Now, I do believe that, with this, it was, there might be some instant kill bombs in here. No, there's no, yeah, there's instant kill bombs on the bottom right here. So if you can see right at the bottom, it's like red. Those are instant kill bombs. And so you have to press one of these buttons to create a chain reaction to get rid of these bombs. And if you press the wrong button, some of these bombs are vertical underneath here. So you have to press the button that has the horizontal bomb underneath it. If you press the button that has a vertical bomb underneath it, this button right here, it instantly kills you because the explosion comes up from the button and gets you, right? Let's see, what else do we got here? So more like little chain reaction things, right? Little explosion, right? The level's kind of exploding behind you, and you just have to run through before you die, right? So, oh, this is kind of fun. So, right, creating this, right? So you trip the bombs, and then they have a little delay, but it creates this really cool kind of like trailing explosion behind you, right? That's kind of fun. What else do we got here? So here we can kind of demonstrate that you can break tiles with your head, and to like, right, we can destroy, some tiles can be destroyed with your head, and when you destroy them with your head, a lot of times they'll leave behind like a scaffolding you can climb, which I thought was a really fun kind of mechanic. And so all this stuff I want to re-implement. Okay, so here's one of our kind of simple levels, right, where you have to press the correct button. If you don't press the correct one, you die, right? So we have, right up here, we have these pillars of death on the right and left that are going to come down and crush you if you pick the right or left, and you have to pick the center. And it's designed so that the center looks like the scariest option, because this one here, it's designed to make the center look like the scariest option because it has all those bombs. But the options on the left and right will kill you. So there's actually two level designs here. There's slight iterations of each other. What else do we got? So we've already seen this on my tech demos page, of like this little chain reaction that can make a little bridge fall apart, which I thought was fun. So yeah, just a lot of really cool stuff. So anyways, that's that. Let's go back to the code stuff. So bottom screen, let's close this. And yeah, I'll share more of this kind of stuff later. Yeah, I guess since there's a lot of stuff, I guess what I'll do is I'll ask people, like, pick a random number between 1 and whatever next time. So now that we have like these tests done, I have to figure out, well, what's the next step here? And we can look at our agenda for that. So let's look at our agenda screen here. So to do confirm pixel values on texture memory, we kind of did that. And one more TauSync unit test for good measure. So we did, oh yeah, we did that. That's why it's blanked out. So 21 we did. So let's edit this really quick. So let's take these two items on the top, and let's just kind of like delete them, because these lists are kind of getting big. So let's just delete those two items. And we need this inclusive rectangle functions, right? So let's kind of add in this tau type rectangular inclusive code here. So let's go back down here, and let's should we close stuff? Yeah, I think we should start closing stuff, because we did all this stuff, we figured it out. Let's get kind of a fresh slate going here and close everything. And the first thing I want to show you is the main C11 file that we're compiling. We have a big list here of all the different system names. These systems are compiled in exactly this order. And the reason for that, or they're included in exactly this order. I don't know if compiled in this order is the best thing. That's probably true, but you know, maybe it's not. The idea when I built this system is to have a very strict dependency ordering, right? So this system cannot reference any of these systems, right? This system, since it's declared here in the chain, it's not going to reference any of these systems. So when you're trying to figure out the relationship between the different systems, if you want a high-level overview, you can look at this list, and you can get a rough idea of how everything goes together. Also, the project was built in mind of having this layering approach, where you see how they all have these different numbers? We can compile up to only here. We can take only these and compile up to here if we want to if we want to use the number 14. So if we say libchan current and we put 14, we'll get a project that doesn't have any of these systems in it, but we'll still have a running project. And the idea behind that is sometimes you end up with just weird problems in your code that are like almost impossible to debug because you introduce some type of weird behavior. Let's say you don't know how to use atomics correctly and you have some type of weird multi-threading issue. That could lead to some really weird undefined behavior that could be almost impossible to hunt down. And to make it easier to hunt down weird problems like that, we can say, okay, when we compile up to here, we get weird behavior. let's compile up into the middle. We'll compile to here, and then, oh, we don't have any problems, right? So the problem is somewhere between here and here, right? So then, since we know the problem is somewhere between here and here, we'll split it, and we'll be like, does it work when we compile to here? Let's say that it does work when we compile to here. That means that the problem is somewhere between here and here, right? It doesn't work when we compile to here, but when we compile to 12, when we compile to 12, it works. When we compile to 18, it doesn't work, right? And so now we can search this space and keep on splitting, right? We can do a manual binary search. So then we're going to compile to here, see if that works, splits, and continue this pattern until we get down to the offending file. Food times, huh? It's food time. Okay, so I guess let's, we're at a pretty good stopping point because we found the bugs that we were looking for. So let's see if any of the people that I like on Twitch are on right now, and so we can kind of forward you off to them with a raid. Let's go see who is who's on. So Twitch. So there's some people I've been meaning to do a raid with, but they're never, like, on when I'm ready to stop. So I'm, like, hoping that eventually they'll be on. But I'm guessing a lot of people... Okay, so I'm guessing a lot of people are kind of, like, doing Christmassy stuff. I really don't want to do Christmassy stuff, but I'm being conscripted. So, yes, so I'm being conscripted. So, I see I got one person on my followed channels. So let's go take a look at them really quick. I think that's what we're gonna throw you, because I don't have anybody else who's on. So let's, so, you know, you may or not like this, but let's just throw you this way, and, maybe you like it, maybe you don't, but, I gotta go, so, thank you for sticking around. We'll do some more stuff maybe later today or tomorrow. We've only been doing this for 3 hours. Usually I go for at least 8 hours because it's like a work session kind of thing. But today is like there's Christmassy stuff going on, screwing with our stuff. So let's do /raid, and then I pasted their name because I want to make absolutely sure that I got that correct. So so let's see. So yeah, have a good Christmas or whatever you like to celebrate. And I'll see you around, and thank you for sticking by.